Okay. Should be able to hear now. Sorry about that. Just make sure you talk loud.
Okay. So this has been evolving. And if you're just curious, this was the 2018 version of this. And as a result of your feedback, and probably today or tomorrow, you will receive something like this. I have been learning to deliver this more efficiently, better for you, more close to what really matters to you. So as a result of that, this year we split the workshop in 3 little workshops. And as you probably saw, you can register for one and not register for the second and third, and you basically select what really interests you. And they are kind of self-contained, so but they follow a progression. So if you feel comfortable with this, you probably will never sign for this. You will sign directly for the Python if you're interested in that. If you're interested in machine learning and you know Python, you jump directly to the third one. So so this one is, let's say, kind of a smooth land. So we will go kind of slow. I will try to offer something challenging for those who probably know a little bit this, so you don't get bored too much. But understand that this is trying to create a foundation for everything that we'll offer you during this 3 weeks. So if you want, you can use the QR code to download this page. We will follow these lessons. I'm using the template provided by Software Carpentry, but basically most of the content is mine. I acknowledge NSF. This is training.
Yes, there's no marks anywhere about it here. So.
It's partially founded by NSF through an MRI grant. Okay. And there are some examples, some code, some files. And at due time, you will know what this means to execute this command on a machine. For the most part, you're free to use your own machine. If you have Linux, Mac, Mac OS, and you feel comfortable with that. But I assume that you are connecting into the cluster where we have everything set up for the lesson. The only exception where the cluster is a must is for this, for episode number 5, where we are using environment modules and the job submission from here and beyond. We assume that you are using the cluster.
What's that? It's at the very top.
So at some point, I will tell you to execute this. If you want to go back and get the code, this is what you want to use. So let's put in context a little bit what we will showing to you today. This will be like an exploration. So you will start moving down to the rabbit hole, kind of, from your computer into the cluster world, into the HPC world. So we start with your own computer, with your desktop, laptop, wherever you are using, and trying to understand how that machine is different from an HPC cluster, a high-performance computing cluster. At that moment, I will introduce you how to connect into that cluster and start executing commands. So that goes into the second episode about the command line interface, where you use that. A few comments, so you start feeling comfortable with that way of interacting with that computer. After that, we jump into text editor. I will show you 3 text editors that you can use in order to create small text files and editing files, things like that. After that, we will have our lunch break. And for the afternoon, I will mention the environment models, a way for a machine that is big and is intended for a lot of users, more than 100 users we have, to change their environment and use different codes and use different set of configurations in order to pursue your research, what really matters. A little bit how to compile code. So I'm not expecting this year I strip entirely everything related with actual development. So I will not, except for the Python, but I will not talk about Fortran, C, R, or other languages like that. But I will show you how to take code and compile it and execute that code. Imagine that you're a researcher, you don't know how to code, but you received something and you need to execute it, and you need to get results of that. So show you how to compile that code, and how to submit jobs, how to put a cluster to work for you, for your research, for your task, and how to get that feedback with the executions are moving for you. For tomorrow, I will show you a little bit of more advanced things, so you could use them or not. So it's the software container singularity. This is the equivalent of Docker containers in the HPC world. So a way of holding something similar like a machine where you have a very good control on the software that is installed on that machine. With the data and codes and everything. So isolating you for the special cases where you will like to take advantage of that. Conda, that is a popular package and environment management. I will show you a little bit of version control. This could be important for you if you're writing your thesis, having some code, the scripts, and you would like to control those versions. I don't want to see people writing, this is my version 1, version 2, version 3, version 4, based on working, not working, almost working, working bad, and after getting lost on your scripts, on your code, on your text, and your papers. So this is a nice tool for you. And it's part of the tools that we offer in research computing. I will show you about that time. Transferring files in and out of cluster. This is an important topic. We will show you a little bit how that is done. And at the very end, I will show you a little bit of shell scripting, a little bit of more advanced things in how to extract data with very simple commands. So with shell scripting to automatize for doing loops, min shell, awk, grep to extract data from text files efficiently. So let's start with this. Let's go down to the right hole. And we'll start, and this is very practical. So I expect you to start doing things. So I try to adjust the time so you can have the time to do things. Maybe you don't have enough time, but I will try to keep a good pace on this. So I don't expect you to do what you have been doing for the last 5 minutes, just watching. This is not a movie. This is more like interactive procedure, I say. So the first thing is try to get a comparison between your computer, whatever you are using on, if you are using this machine, it's fine, and what we have on our cluster. So here is the procedure to get, if you're using this machine, will be something like this, to know what this machine has, especially the processor. So go and try to get an idea which kind of processor this machine has, your machine has, or your laptop, your notebook, whatever. So this is one thing that we are interested in knowing in order to compare with an HPC cluster, the amount of RAM that we have, so the amount of memory live memory that the machine has to perform operations. And a little bit more details that probably in Windows are not so simple to get. In the case of Mac OS, you get a little bit more. Well, this will give you, again, the processor, the speed, and we will talk about those terms. I would like you to understand, start getting a slightly better understanding of what a machine is and what matters to a machine in the performance point, from the performance point of view. The amount of memory, hopefully, if you have a Mac or Linux, you get a little bit deeper and get a few more data like this. The cache, level 3, level 2, and usually they don't mention level 1, but you can infer that, and we will see that later. And again, the memory of the machine, those are important numbers, and we'll talk about them in a moment. And in Linux it's easier, but from a graphic user interface, kind of a mess, because it depends on this Linux distribution that you are using. If you are using Linux or Mint or Ubuntu or Red Hat, is slightly different from a graphic user interface. So I capture a little bit of that here. This is if you are using something like Ubuntu or the KDE version of Ubuntu or Linux Mint, whatever. So in particular for Ubuntu, this is one way of getting the processor. Try to capture this number. We will use this number. For example, this machine is Core i7 3770 CPU 3.4 gigahertz. So try to write that on a piece of paper, something like this. Try to see on that machine, because we will use it in a minute. We will I'll use the browser and check a little bit the internals of that, what that means. For example, in Linux Cinnamon, there is something called the system info, where you get something like this. And there is another, this is again Linux Cinnamon, where you get the CPU, the RAM, the graphics card eventually. So you get a little bit of data. From the command line, and this is skipping a little bit on what the stage that we are now, you can get this information easier if you like. You can execute this, cat proc CPU info on a terminal. We will talk about that in a minute. And you can get something like this. And this is actually all that we need. The model here, the speed of that processor, and a lot of extensions. So we will talk about them in a minute. The amount of cache. This is important. This is extremely important in HPC. So we will talk about that in a minute. And you can see the memory with this command. There are more commands. There are ways in Linux, Unix, to get deeper and deeper and deeper into the system and get more tiny little bits of information. I will skip those things right now. And giving you the opportunity to start copying that CPU model. This is something that we will use in a minute. Let me explain you a little bit what it is. We live now on a very special moment in history, kind of, for the HPC environment, high performance computing. If you today wants to buy a cluster, there are not too many options. So, and most of the clusters uses either Intel or AMD processors, and tiny little fractions uses something else. Cray, IBM, special machine, vector machines, those are relegated to a tiny little fraction of the market. So if you are working on this now and you will move into something in the future, in the industry or in a national lab, in another university, whatever, the most likely situation that you will face is finding another machine like this. Another machine, another cluster, big aggregate of computers with those two manufacturers, Intel and AMD. So for most part, they are the same manufacturers for CPUs, for processors, for consumer level products, like desktop computers, something like this. So, and nowadays, knowing which processor is better than other is kind of tricky. 10 years ago, 20 years ago, you just basically see one figure. And the manufacturers push into that direction to see just one figure, the speed of the processor. At that moment, every 2 years, that speed doubles and doubles and doubles until beginning 2000s, something like that, where that pace stop or decrease. So the marketing people were scared about, well, I cannot sell this, just saying that it's 2.1 gigahertz, and next year sell a new one that is 1.9. So people will not buy it. So let's change the marketing structure and let's put the people with a different number, something, let's call it Core i3, i5, i7, and now they have i9. So they have 3-4 numbers, and they see those numbers, and they figure out that bigger the number is better, or they always assume that the consumers are dumb. So put things simple, or they put max or hyper or super powerful gamer performance or something like that. But that has changed. So all that you see is Core i3 and a weird number. This weird number. From looking at this number, you don't know if this is this is better or worse, if they have 27, 60. You don't know. Another thing. The reason why the processors are not getting faster is purely and simple thermodynamics. If you start increasing the CPU clock, the energy consumption increases non-linearly, and power consumption means heat. You need to dissipate that somehow. So at some point, if you try to get a machine with 10, 20 gigahertz, you're pretty much reaching the temperature of a nuclear plant. So you don't want a nuclear plant on your lab. So that's why they changed that. They preserve the speed of the processors, and instead of that, they are adding more and more replicas of the same chip on the same piece of silicon. That's called cores. Those are actually processors, but it will be again confusing for the typical consumer to call a machine that it has a chip with multiple processors. So they change the name and they call it cores. And now you see most of the machines have 4 cores. Machines nowadays appear with 6 cores. Probably your phone also has 4, 6 cores, things like that. Normal machines start getting more and more cores. The speed has remained the same again. And they perform better for other reasons, not just pure speed. And in the future, and you will see the clusters that we have now, they have 40 cores on a single machine. 40 cores on a single machine. And in the future, you will see machines with 60, 128, 200, and in a few years, probably they just count in thousands of cores in one single machine. So this is the status of that. Another thing that people who designed those processors did was creating something called hyperthreading. Hyperthreading is basically saying to the operating system that the processor is smarter than the operating system. So I will tell the operating system that I have more cores than actually the machine has, because I am able to reorder the operation somehow with that lie than just telling the truth to the machine that I only have 4 cores. So I tell the machine I have 8, they will try to push me load task for 8 cores, and I will manage, the processor will try to manage that extra load better. And the point is that this is okay, this is actually a good strategy for desktop usage, where you basically have a browser with a ton of tabs. This is what I have, a ton of tabs, and probably I have my mail system here, I have those different communication things, Skype, whatever. A lot of tiny tools, and they are sharing time for the process. This is very different from the kind of tasks that we execute on an HPC system. On an HPC system, we are crunching numbers over and over during hours, days, or even weeks in order to get a result. So typically, it's not a good idea to enable hyperthreading on a cluster, especially in a general purpose cluster. So our cluster is a cluster that is serving people in genomics, as well in physics, in medicine, in Davis College, in agronomics, in all different disciplines. So we basically need a machine that serves well everybody. So we decide, for most part, for at least for the compute nodes, we disabled hyperthreading from the very beginning. So we are not using this. So what you see is what you get. You have 8 cores, it's because this machine actually has 8 cores to work on. Now, CPU frequency. This was the thing that was doubling every 2 years, 20 years ago. So this used to be the most important feature, not anymore. But they have been getting extensions, something like this, that allow the machine to execute several instructions in one cycle, in one clock cycle. So the machine is able to do more at the same speed thanks to this. In our new cluster, we have this. In our previous generation, in the cluster that we will be using, we have this, AVX and AVX2. And gamers used to do something that we are not able to do, overclocking. So what they do is basically they artificially push the speed, the clock speed higher than the manufacturer did or announced was the safe value for that processor. And eventually they compensate with liquid dissipation, more fans, and if they are crazy enough, they just submerge the whole machine in liquid nitrogen. So if you have enough cash for that, cache. This is important, and that's why I ask you to copy this for your machine, for these text-to machines. try to get this because sometimes the cache size is something really important in HPC, and it's kind of hidden under the rug for consumers. It's too complicated to mention that to consumers. But you are not consumers, you are researchers. So I treat you with respect with that, and I will not put this under the rug. And this is an important, the cache. And actually there are several. The cache is a tiny little memory that sits very close to the processor, to the core. It's actually in the same chip. And it's intended to store data that moves quickly into processing units. So again, a cluster is intended to crunch numbers for a long period of time. It's very likely if you are doing what actually are HPC codes, high performance computing codes, they usually reuse the same data really close. So they have some kind of locality in the data, including temporal locality in the data. So you can reuse data easily. So if that data it sits close to the CPU, they can reuse it. And they don't have to bring the data from RAM, or they don't have to bring memory from the hard drive. All those things are one order or two orders of magnitude slower than the cache. And they have different levels. Typically, cache level 3 is a piece of memory that sits between the cores. So all the cores see the same memory. Typically, this memory called L1 and cache L2 are for each individual core. So when you see this, you will get the idea. Okay, so now let's go to exercise 2. Go to this page. If you are using an Intel, most of you probably are, but people online, maybe they are using their own desktop computer, so they could eventually use AMD, but I will show you how this looks for Intel. I will copy this number here, and I will go here and paste that thing. And I will get all the data that is actually relevant that let me check sometimes this is what happens. They have several generations for the same thing. So copy these 2 points. This is V3. Okay. So this is V3. So it's this one. So you will get different results except if you're using the Dexter machine, you probably get the same result, so the same processor. And you can see when this machine was launched, was Q3 of 2014, and the price, whatever, the speed, and they have something that is called the turbo speed. What it means is that when they notice that the execution is mostly serial and only one core is in usage, they start disabling other cores and putting more energy on one single core and increasing the frequency of that. So this is a way of compensate. So, but this compensation is not free. You are disabling some cores in order to get that. This again, in many cases in HPC, you don't see this because all the cores are in use at some point. They will also tell you the amount of power that this is using. So now imagine, okay, this is using 120. 120 is kind of those poorly energetic incandescent bulbs, lights, something like that. And now you have two of those on one single machine, and we have a rack, something like 3-4 racks, with 20 of them. So imagine having like 30 volts, those emitting heat permanently for hours, for days, continuously. So this is a lot of heat generated, and that needs to be dissipated, and typically by air. And the cache projects around here. Cache. They tell you that. So again, you start getting a little bit of context of what a machine is, what they have, and what this means for high performance computing. This is one of the key elements of this. Another is the connection. What it makes different a machine, your machine, from an HPC computer is that an HPC computer has hundreds of machines like you. Much better, actually, machines than you, except if you're a gamer, but a very good gamer, a very wealthy gamer, actually. But they are interconnected with very exponential networking for them to communicate very efficiently. So now let's jump into this. Connect to the cluster. Now you have received this. People online have received something equivalent to this. And I will show you several ways to connect to the cluster right now. So this is the first thing, jumping into the cluster. So the first thing that I will show you is with a program called Buddy. This is the simplest way. If you are using Windows, if you are using Mac, you don't need to do this. If you are using Linux, you don't have to do this. I will show you just the way of entering a cluster, entering this different world from this program. Training. This is what I received. So this is the first. Again, if you are using Mac, all that you have to do is open the terminal and execute the command that you probably saw here. This command, SSH. In your case, username will be training1, training, whatever you got, and the host name will be spruce. Spruce.hpc.w.
Can you show, because you had your system saved, they didn't see how you actually type in host name and all that.
Ah, okay. Let me do it again. So, well, all that you have to write is this. Probably it's too little, too tiny, but you have to write here spruce hpc w edu.
It's on your sheet.
Yeah, so the first line of probably is the same thing for people online, right?
Yeah.
So the first line contains the host name. Question, yes?
Well, I tried to log in and it's asking me now for, on top of the password, asking for an LDA key password.
It's because you typed password in wrong. I know it looks for, it's because it's the trading account. So you hit enter on that. If you hit on that, it'll flip back around to it.
Okay. So this is the host name. This is the machine we are connecting to. They use ports, so they connect through something called ports. so different venues to connect to the machine. What I did was, what Nate did for me was to save this configuration under a name. So I put the name this, and I save it. So, but what actually matters is to enter the host name here and keep this 22. It's okay. This is the default, and it's good. And just click open, and it will ask you login as. And at that moment, you use the second line in your piece of paper. I got training 001. You got training something else. And it asks me for the password. I want you to have a secure way of getting into this. So I am showing you this is the let's say, one way. I will show you another way that is slightly better. So you have an alternative. I give you alternatives, you will help yourself on this. So you should get this. Actually, you get something like this. You get a lot of message, a big message, legal message, banner, whatever. And at the very end, you get something like this. Training 001 at SRIH 0001.
You have Mac or Linux is going to show you, so don't panic.
Yeah, if you are in a Mac, it's very similar.
Anybody else stuck? If you are, this is key.
This is key. If you get stuck, we will not move from here. I don't care if we are a little bit out of schedule, but I want you to move.
He's going to show Mac. Oh, yeah, don't worry. I know that's a little confusing. He's showing Windows first because I'll review here on Windows. But if you have Mac or Linux, Guillermo will show that next.
Okay.
So don't feel like you're behind. Everything's all right.
Okay. If you are using Linux, you probably know how to get a Linux terminal. That changes from distribution to distribution, but you should get something like a console, terminal, extern, GNU term, G-terminal, something like that. The name changes, but it's basically a window with black background and just a prompt. This is called a prompt, by the way, if you are not used to this. This tiny little message below here is called a prompt. If you are on a Mac, you can go to utils, it's an applications utils, and let me see how it shows here. Utilities, it's called utilities. It's just called terminal. So that's from a Mac. And you get something very similar to this. And imagine that this is the Mac terminal. All that you have to do is SSH, training 001 at spruce.hpc.wpu.edu and execute.
This is the actually most difficult thing in the next 2 days, so don't. Once you get past this, get logged in, everything else is working.
So we're basically hitting the door. After Alice entering in the rabbit hole, we are hitting the door to enter in this wonderland, if you like. So the door could seem tiny, but what is behind that is interesting.
Wait a second, I get it back on.
What?
Wait a minute before I get it back on.
Yeah, maybe we can take this moment and show you another way. So you start getting the alternative, and we will pause a little bit and get this. And again, I am learning with this. Let's say adjusting the time and expanding my lectures now. So my timing probably is not good. and I'm learning, and you will teach me when I'm doing something wrong, when I can do something better. You will give me feedback at some point in time. So I want you to be in for this. So I will show you another way, and you have to download something. It's this one. This is an alternative from Windows. From Windows. If you are using Linux, you don't care about this. If you are using Mac, there is something that you have to install. There is something that you should install. If you are using Mac, and it's installing this on your Mac. With this, you will see Windows from the remote machine popping up on your desktop, on your computer. So not only will allow you to connect, but I will also allow you to see Windows. And we will do this not very often here for this training, but for next week, for the Python and from the machine learning one, we will like to see plots somehow. So this is something that you would like to see. It's not necessary for this session, for today and tomorrow. You don't need it. So this is a bonus objective, if you like. And on Windows, you can install this one. It's called MoveXterm. There is in download here, there is a free version and there is a portable version. What you get basically is a zip file. This zip file, you want to compress that zip file and you get this executable right here. That's all that you need. You don't need to install anything. You just compress that and you execute. And this has the advantage of let me do it. Okay, that's okay. Rolling topic. This gives me from Windows the ability to write exactly the same command that you on Linux or Mac are able to execute. Training, so on. Okay, the only reason why I didn't get any message asking for a password is because I stored it a few minutes ago and before we start. So I got directly into this. The advantage is, let me see if this will work, is that I can get tiny little windows like this one. Let me see. Like this one, popping on your screen. This window was generated on the remote machine and is sending you back that. So, and this is one way of testing that you are actually getting what is called X11 forwarding. So, going a little bit technical, this is. You just showed something else to me.
It's fully for next week. You're not showing the stuff you're showing now. You don't need right now, right?
No, I'm showing this is a plus for this session. This is a must, so very good, very strongly suggested for the next week and the machine.
We'll demo this again next week. So we'll show how to install it.
You need one way to get into Spruce, either PuTTY or MoveXterm. Or if you are using Linux directly, if you are using Mac, the terminal, the Mac terminal, you need to be in the machine, into that machine. So that's another way.
Everybody else good?
So again, the only difference between using mobile extern, apart of some niceties, let's say, but really the difference is that a mobile extern is an SSH client attached with that X11 server. It means that allow you from Windows to see actual Windows, let's say this kind of Windows, from remote computers. We don't need this today, tomorrow. We don't need it. So if this is cumbersome, forget it, use PuTTY, it will be okay. Another thing is that they ask me the first time if they want to save my password, and I say yes, and every single time that I'm doing this, I don't need to enter my password. So I will probably be using this way just because I can get better fonts, bigger fonts, so everyone can see this. And I will be jumping. I will be jumping here a little bit like crazy. Here. So the class, we have two clusters: Spruce Node and Thorny Plat. Thorny Plat is the newest. And accessing that cluster is a slightly bit more complicated. So we decided to keep this simple because the cluster, the newest cluster is not here in Morgantown, it's in Pittsburgh. So getting access to that cluster involves another intermediate gateway. So it will be a little bit more complicated. But everything that we will be doing here, we can do it on the newest cluster. It's okay. So what you will be using is this. You train an account, and the host name is this one. If you are connecting to Thorny Plat, just for you to know, and again, you can request accounts. Probably, if you don't have accounts for us, you can just request an account. You just need, if you are not PA, you just need some PA to acknowledge that you work for him or her, and you get your account on either Spruce or Thorny Plat. And again, the difference is that we have an intermediate machine, so you have to jump into that machine in order to jump into a Spruce due to security reasons. So this is what is called a prompt. All right. The first thing that you need to know when you enter the door is to know how to leave that. So exit. If you want to execute it, it's okay. If you don't want to suffer the pain of writing the password, just know that you can live with this. But I will. It's okay for me. I have my password here. So, and I get it. Okay. So let me see. So you exit with this. And now I want you to execute this command. So I want you to be sure that you successfully get into a Spruce. I want every one of you, every one of the people who is attending this online to be on a Spruce. So how I check that I'm in is because I see this. This is my prompt. This is why it's telling me who I am, where I am. And I basically ask you to execute this command that will do nothing, will show nothing. We will see what they do. This command, and eventually this command. you should be able to see this. And eventually, if you want to execute this, you should get exactly this. Again, we are going slow. If you got stuck, it's okay. This is something that you are not used to, especially if all the machines that you have been using are Windows machines. So you probably are too comfortable with Windows machines. And this is an entirely different world. This is Wonderland. All those are commands. And things that you write, you delete, and the computer doesn't care about what you write until you hit enter. If something is not right, they will tell you the command is not found. Otherwise, you will execute something. Try this one. And we will see this in a minute. But I would like to be sure that everyone, if someone is not in, if someone is not entirely sure how you got into this, please raise your hand or mention it online on the discussion. I would like you to see this. Very similar to this, you will execute this command. This is the calendar. You can start playing with this. There is something like this. Execute this. Cal -y. And you should be able to see something like this. Like that. This is a command. And those things with dash something are called arguments. Those are things that modifies the command, produces a slightly different result, and you need to know what the result is. So cal will show you just the current month. Cal -y will show you the entire year. If you want to know, and this is why this is difficult from the very beginning, is that one thing is to know more about one command once you know the name of the command. But if you don't know the name of the command, this is when things become hard. So when you know the command, but you don't know exactly what kind of things can I do with that, what kind of tricks I can play, there is something called man. And I can put the command. And I will show you this in a moment. I just want to be sure. Okay, it's 10 o'clock. So if you want to see this, there are several options here. And all those options are basically, I was using this one. And you can play with those and start getting a slightly different results, more months, different years, whatever. But it is time now. Now it's 10 a.m. By the way, when you execute something wrong, you probably hear that thing. All right. So this is good. If you hear this, because you are doing wrong, and if you are doing wrong, it's because you are learning. Otherwise, you should not. If you are not learning anything here, you're not supposed to be here. So let's go here. Okay. So let's jump into this one.
Before we get into that, make sure everybody's
everybody's the same page.
So how do you get back out of that?
Yeah. For the manual page, yeah. So I was here and I execute Q to leave. Please ask me those things. This is second nature to me. I've been doing this for 20-something years. So for me, I don't think about that. My fingers know about those commands. I don't care about them anymore. But yeah, it's just time. It's just time, practice, and 20 years. So it's okay. It's okay to ask those things. You leave that, you execute it.
Also, explain that you won't, when you type your password in, you won't actually see it type.
Oh yeah, yeah. That's actually a good idea. Yeah, typically when you execute commands, for example, when you execute a web page, you don't want to see that command, your password being exposed to someone looking on your shoulder, right? Pretty much the same idea. When you execute, you type your password on the terminal, you see nothing, and it's okay if you don't see nothing. So it's for your own protection, let's say. So it's okay. If you make a mistake, it will say the password is wrong, type it again, and you type it again. You make another mistake, you say password is wrong, and they kick you out. And you try again. Okay, so this is the command line. And this is our interface to the computer. There are several interfaces to computers, and there are several today. So it used to be like this, and it still is like this for HPC clusters. It used to be very different 40 years ago. 40, 50, maybe 50. It depends. The way you interact with that computer was with the card kind of like this, with holes, and you have to keep them in the right order. And if someone wants to trick you or do something very nasty with you, they just mangle with those, change the order, and your entire procedure is gone. And you basically feed the computer with those punched cards. And eventually what you see were those noisy printers, those that go up, right and left, very noisy, printing your results, your numbers for your simulation. That used to be the interface. And if you go 60, 70 years ago, your interface with the computer were 6, 7 ladies who were the actual computer programmers who basically switch cables according with the program that they developed to operate the computer. So if you go back in time, you will see the 6 ladies who operate ENIAC, I think. It's ENIAC? I think it's ENIAC who operate that machine. ENIAC is in Philadelphia, right?
What's that?
ENIAC. I don't know. All right, those old clusters from the old time. But now you have this, something like this. So you have another interface with a computer. This is basically a computer. Is your finger. It's another interface. And if with time, you can eventually be able to explain to the computer to just speak to it in normal, in natural language, the kind of things that this IBM project Watson does. But we are not there yet in general for HPC computing, not right now. So we interact with computers via command line interface. It's light, it's easy when you learn it. So it's hard to learn it, and that's why you are here. But it's very efficient way of executing things in a computer. And lighter from the computer perspective. So all that you get is something called a prompt. Typically, on my lectures, I identify the prompt with the $sign. So when you see this, you are not supposed to type this $sign. You are supposed to type whatever is after that. This is my indication that you are doing this on a terminal. This prompt, this $sign. The actual the actual prompt that I have is this, the $sign with something behind. And when you start executing commands like this, and you see, if the command is not right, it's not right. The computer will not do any guessing on what is the command that you want. If the command is wrong, it's wrong. You get this. The command, when you hit enter, the command is executed on the computer. Whatever it's meant to be displayed is displayed, and you get your prompt back here. That's how you interact with the computer. Something is wrong, you get this message. Usually not getting anything means that everything was okay. In many times, that's what happened. Why you want to use this? Let me put you with a metaphor that I always use for this. Imagine that you have to put the banner message on 3 images. You receive 3 images, and you have to put some message. This molecule is this, or this image is from this kind of insect, or something like that. A tiny little message. So you open whatever is your image editor of your preference, GIMP, with this very popular Photoshop, whatever, I don't know, and you write that. You click some things on computer, and you type that. So in a couple of minutes, you get the job done. You have 3 images, and you have to tag them, and it's okay. Now I change you the task. I give you 10,000 images, and I give you 10,000 tags that you have to associate to each image, one by one. Of course, you cannot do it. Well, you can, but you will spend your next months just doing this, to tag in that amount of images. It's a monkey job. Or you can create a script, and you can execute this on a command line to tag those images efficiently. Of course, Photoshop, those computers, they have scripting capabilities. That's another way of doing it. But the command line gives you the ability to perform repetitive tasks very efficiently and change tasks and actually program that. That's the very end of this workshop. We will show you a little bit of shell programming. And here is, so that's basically the reason why you want to use the command line interface. Because at some point, once you learn the commands, you can automatize things in ways that you can never do if you are just waiting to hit with the mouse over and over. I give you an example here. You don't need to understand this. This is kind of gibberish right here.
Can you zoom in when you're around?
Wait a minute. Let me see. Like this? More?
Maybe one more time.
One more time. Okay. Okay. Yeah. Okay, so I will take this. Let me see if I can do this without actually writing it here. Yeah. So if you are using more external, I don't know if that will work with Buddy. What I did was this. So you don't have to type this. You will not learn anything. Just type it. I just mark it. I copy. I went to more external, and I paste it. They they give me an option for paste. What I did was basically clicking the central button on the mouse, that is paste. So that's the command. So this is a very simple thing. With right now a very obscure procedure, this, for getting all the numbers, all the squares up to 8,000. So this is a little bit of shell scripting. One-liner, but it's a shell script. And this is the kind of things that you can do when you execute from the command line interface. Again, it's a good exercise if you want to type it. Be very careful when you type this. For example, this symbol has to be like this. Every quote is different. So double quotes, it's not exactly the same as single quotes. It's not exactly the same as those. Ticks. Okay. Yeah, tiny little details matter here. Okay. So let's start. I will teach you like 10 commands, something that give you enough flexibility for you to start doing things. I will not go deeper. It will take me a lot of time to show many commands and probably it's worthless. So I will start with this. There are a few variables that we have basically on any Linux system. You see this. And I hope you start typing this. I will probably show you a few things here. So I will make this. So this is on every single system. Unix, you see this. Those are variables, and you will see about them. Those are environment variables. So echo is just a command to show the content of that variable. So this is what the variable is called home. And when you put a $, you are showing what that variable is referencing to. What is the content of that variable? This user is also very common in Unix environments. And this is very special for us. Scratch. I'm showing you this. It's working for me.
Yeah, that actually does. You actually see to that.
Oh, maybe. Okay. Okay. On your real accounts, you will have that. You will have two places. Your home folder, where you can store up to 10 gigabytes of data, and you have a Scratch folder for you, where you can store whatever you want. After you hit too many terabytes, you will receive a mail from us. Okay, you are in the top 3, and so as soon as you are not in the top 3 or top 10, it's okay. Again, you can put this. You can type and execute commands. So echo is our first command that we will learn. We actually learn a few others at the very beginning: cal, date, postname. So you start accumulating a few. So echo basically show you whatever you want on the deck. But after that, it will show you the screen. It seems silly right now, but it's useful later. Date, show you the current date. What else we can do? Echo and and cat. Okay, I need to do a trick here. Before cat, I will show you this command in order to have something to cut. ls show you the files that you have in your system. Right now, you see nothing. There are actually several hidden files on the system. By hidden, Unix, Linux, then doesn't mean to be secret or protected by any means. It's just files that you typically don't need to see. But you see, if you execute this, you can access them. There is one that we can see right now. When you execute this ls-al, you see all those files. I would like to see just one, and cat is a command to see the contents of a file. So you write cat, and after space, the space is important. The number of space that you add is not important. But you have to create one. And again, you can move this up and down with the arrow keys. And when you feel more comfortable with this is a little bit more advanced trick. You can go to the very end with Control-E. You can go to the very beginning with Control-A. So this is very useful when you start doing this a lot, 8 hours a day. So you don't want to start hitting the arrow keys as much.
Can you repeat that, please?
Control-E to the very end, Control-A to the very beginning. You see that this tiny indicator here show me where I am writing, where I am. I just started entering here. I will be writing on front of that. If I go to the very end, I will write on top of that at the very end. So this square will show me where exactly I'm located to where things will appear when I still hitting keys on the keyboard. And I execute this, and I got message, sorry, there are no such file or directory, because the file that actually exists is this. Okay, let's create one here. Another trick. You can use, right now you are here, you can use the arrow keys up and down to show you the commands that you have been executed before. So you can go up, 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 and execute the command and see the commands. So all my history of commands is stored, and you can basically go up and get the command. There is another one. When you execute the previous command that we execute with that. And let's do this thing. I would like to create one file with this content. There is a small trick in the command line interface to redirect the output that originally we will see on the screen, redirected into our text file. Ready that. And let's say that I would like to call it hello. And I put in the txt just because I assume most of you are familiar with Windows environments where the extension matters. For most part, in Unix environment, the extension is completely optional. And many, many things don't have extension at all. So what I'm doing here is redirecting this hello world into a file that is called hello.txt. Let's see that now ls will show me one file on the system. You will see one file on the system, one visible file on my current location that is called hello.txt. And now I can go back into the other command that I show you, cat, to see the contents of that file. Let's see. Okay, this is nice. As I show you here, let me see, like this one. The command line interface is an entire programming language, actually. And you can do a number of things, especially if you are not involved with real numbers. For integers, you can do a lot of things without getting too much trouble. Another thing that you can do is doing some math. Let's see, 21, 22 plus 45 times 2. So as a very tiny calculator, it's okay. You are executing the operations. And you are getting the result. Everything fine here. I would like to see that everyone is able to get this result, and everything should be working.
So if you got, hopefully everyone can hear me, and you're going to repeat this, but if you get stuck in cat, hit Control-C, go over what Control-C does.
Oh, well, yeah, if you execute cat, but not execute anything like a file of that, you got stuck, yeah. And that happens a lot. They have many commands, they expect something, and if they don't get anything, they start expecting something on the command. So typically what you can do is Control-C, Control and C, both together, Control and C, and you exit from that command. So it's okay, I do it all the time. Control-C, kick me from that.
Basic Control-C kills what you're currently doing.
Yeah.
But I will get it. There's signals in the back end that's sending it. So if you get a command you're executing that's stuck, and it might be using MATLAB or anything like that you guys might use to, if it gets stuck, you can use Control-C. Now, you don't typically want to do that, but if you're, for this type of stuff, it's completely fine. But if you get stuck, that's one way to get out of it.
Okay.
Everything else is good?
Yeah. We are good? We're fine?
We're on schedule, so we'll get far behind, doesn't matter.
Yeah, we're actually right now, and for this first part, we're fine. So again, these kind of things can go into more math. And except for those first parentheses here and the last parentheses, this is the actual math, and the parentheses have the meaning to encapsulate operation that otherwise will be executed in a different order. So what is happening actually is that the computer is executing this, and whatever is the result of that is associated to a variable that is exposed with the echo at the very end. So for this, it's okay. But don't expect to do something like this. You start playing with real numbers, with floating point numbers, what they call, And no, sorry, but no, it will not help you with that. So bash scripting is okay, especially to move files, to iterate, to do some trickery with files, numbers, things like that, but not for actual real scientific computing. So for that, you have to use something better. At least one other scripting language like Python. You can do it. It is possible, but it's different, and I will not show you that here too much. So if you are curious, there is something called DC, that is a calculator that actually is able to do this kind of thing. So, but this one uses reverse Polish notation. So I don't know. It depends how old are you in this business. When I was back in college, we used to have those HP Hewlett-Packard calculators that were able to do reverse Polish notation. So, but nowadays people use just cell phones and they have normal calculators or things like that. So these kind of things are not used too much, but interesting. So if you want to play with real numbers, this is one way. So using the DC calculation. And let me see. Oh, this is okay. This one. Nothing the difference between doing an echo and not doing the echo. If you execute like this, you get the answer. It's not a command, because what it's expecting is exactly the same as if you execute this. The echo is just showing what is after that as text. There are, let me see. There are, I am moving up and down and trying to offer you something a little bit more advanced, a little more normal, to try to keep you the spike and all this. There are some extra escape figures here. If I execute it like this, you will see that I got basically a D in the middle, not getting anything interesting. Okay, it's like this. Hello. What is this? Oh. No. Wow. We should be interpreting this. Oh yeah, I have to encapsulate that. So I will mention this in the very end, in the shell of scripting. But just for now, if you want to try, you can play with this. There is this one, the /t, that is basically adding a tab. So it's stretching the space between hello and world. Or, for example, play with this one, that is basically send you back one line. So you get this to the next line. So the way you execute this, you have to put this -e argument. And the way that I was checking that with the man echo, where I got the interpretation of backslash characters with that. So otherwise, I will just get this touch. But this is just for you to play. Let's go back. What? Yeah. Yeah, we can take 5 minutes break. And actually, if you got stuck, if you want to talk to me privately or privately to the, you can do that. So let's take 5 minutes. So 5:37, we will come back.
If you get the manual for a command like this, try it.
I think Lash will show you that. Yeah, but this is different. This is kind of different.
So you can search a manual page by doing / whatever
Oh, yeah,
you're searching
yeah.
for.
Yeah, so if the command is something separately, like ls, the man for that is.
Yeah.
But if the command is something very external to the shell, it will be in the shell. So bash. The way I search for it is with the slash and whatever I'm looking for. The problem with this is that this command have several uses, different contexts have different. So if you're interested in this, and we will talk about this.
Yeah, because you're using it to pipe the output into that file.
Yes, the way this is very common. To pipe what I did here, piping.
I'm gonna ask them.
Yeah. So basically, I'm sending the output of that command into this. There is something else that I can do. So date will show me this, and date this will append the output. So will not delete whatever is left at the very end.
Okay.
So this is very useful when you are executing jobs.
Like create a log file or something like that.
No. For example, I'm doing something in which area are you? Which area?
I'm in medicine.
Medicine. Okay. So, the closest to me is if you were doing some statistical epidemiology or something like that, and you are running some R scripts or whatever, and you want to see the time when the execution starts and the time when it ends, in order to get a feeling if you can escalate this for more patients or more data or something like that. You can put date and this, and at the very end, date, and get the initial date and the final date. So you get how many hours, how many days it took you to get you the results. So, and if I did this for this amount of data, how much you can expect for when I double or triple that data. So this is the kind. That's why I'm showing this kind of thing. And you see that. So I am there. So if you want to see this, it depends on the level you want to see this. Bash scripting. Okay, there are some basic and advanced. This is well known. The advanced bash scripting guide, where they show you the different redirections or the different IO redirections. So this is the chapter, exactly what you are asking me. Is right here. This, and they will show you that. Far more exhaustively. What I'm doing is time compressing. From my experience doing research, the kind of things that I use a lot of time, trying to transfer just that to you. And if you need more, here is the document. Okay.
Is there like a manual of commands that we can see? Like I tried to do man, and it gave me something weird.
Yeah, well, look, let me see. Man. Well, many is the manual. So this is the manual of the manual.
Right. So that's why I'm trying to get just the like a list of commands.
There is something. There is something that you can do. It's actually okay. There is this place. This is a cool place where you can search for those sheets where you see commands or things for different kind of things. So let's see Linux commands. And you probably get something. Oh. Well, this one, for example, give you a nice set. So you can download the PDF and print it and keep it on your desk. And you see this is a fairly good amount of commands. ls, I show you this, I will show you this, pws and pdir. All right, I will show you all this up here. You saw this one, the SSH. I will not enter too much into installation of software, so I will not mention this. Not network because you are not a system administrator, so I will not deep into this. I show you date, call, time. Some of those are more for system means, so I will not some of them. Yes, those again are for system means, for compressing files. Maybe I will show this. I will show this compressing files.
This reminds me of when I was using DOS, like back in the day.
Yeah,
like,
DOS it has a long heritage before actually that. This is actually much older than DOS. And DOS was kind of a very light version of a command line interface for personal computers back in the 80s, something like that. But this has been like that for since 60s, 70s maybe. So what you are learning here has been around for 40 years, 50 years at least. So you can see that it has been around for that amount of time. It will be around for another amount of time. So you are not wasting your time learning these kind of things. They will be around. They will be around. A lot of things have been built on top of this. Your learning is not something that will be obsolete next year because a new Linux appears. No, this is good knowledge. This is something that will last.
And this is the cheat.
And the cheat, and cheatography. So you can get some of those pieces of documents. You see the PDFs are really well produced. So you see they are really nice. You print them and you get the command and you learn. And this is actually the best way of learning those things, to have something and use it close to you, so you don't have to waste time searching all the time with what's the command that you need.
All right, thank you.
Okay. So in this, okay, let's back. Okay, let me collect a little bit.
Thank you, everyone.
Yep.
There's a question in chat.
You go over how you created the hello.txt file.
We don't need to look at the chat. Just go over how you.
Okay. Well, actually, I use. Yeah. Okay. Let me show you another command that is slightly more advanced. That will show me the commands that I've been executing previously. Not just like this, but the entire history. All the commands, they save your history. They probably have a limit to that, but my history probably preserves all the commands that I've been executing in the last 2 or 3 years. So I will see all the commands with Control R, and I start typing the commands. and I execute Control R, and I will see all the commands that I execute with echo. Until I reach the command that I was wanting to show you. Echo. So this command is redirecting the output of the first command into the file that is after the greater than. And the result is this. Actually, and I can do something else. Another way is this one, with double greater than. This is appending the output of the command into the file. If the file doesn't exist, it will create it. If the command, if the file exists, it will just attach this at the very end. Otherwise, every single time that I execute like this, it will erase the file and write that. And I will like this, and you see that the cat command with the hello now has 2 lines. Yes?
You do the Control R again.
It's Control R, and it will put me in, it will show you this, reverse I search. And I start typing echo. And I will start so I will search for everything that I wrote starting with echo.
Right.
And I would like to see my history in reverse. So I start typing Control R, Control R, Control R, R, Control R, 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 until I reach what I want. There is another way. Probably it's not populated yet. Yeah, it's not populated. This, once you exit from the session, all your commands are stored in a file. This is the file where those commands are stored in .bash history. So you can execute cat if you want to see all the commands. But the commands that have been executed during this session are not stored yet on that file. So you will not see them. I see those because probably execute, yeah, I execute those. So this, again, if I execute this, I create a file, ls, hello.txt. The content of the file, I can see the content of that file with hello.txt. And I can start playing with that, with this redirection. And you see that I can attach that. There is something that doesn't work. Imagine that I can do this. If I do this, for example, for this, let me see. Hello. And if I execute it, you see that I am creating this over and over. So I am populating that, appending over and over. But this doesn't work. This kind of trickery of reinjecting the output into the input as well. Let's go back here. Oh, I show you a couple of things to the people who approached me a few minutes ago. And one is, if you want to learn this deep into this. Let me see. There is this. that is actually, you can search for this, Advanced Bash Scripting Guide. I will teach you about this. We will go back at the very end of this workshop tomorrow. I will teach you a little bit of this, Bash scripting. But if you want to jump into the very end of this, be my guest. Another thing is, this is a nice place where if you want to learn this, you will learn these commands now. I will show you just 10 commands. And if you are not using this in the next few days, it is gone. So another thing that you can do is to use this place, for example. They have very nice one-page this kind of sheets that you can use. Some of them are really nice. It's people who actually produce those things and offer them freely. So you search, and I was searching for this Linux command. I got one, and I'm showing you this one, and they produce. They have a way of producing a PDF version of that is nice. If you want, they also offer you the ability to create your own. So you can create your own sheets and offer them to the people. So let's continue. Okay, this is kind of advanced. It's neat. It's kind of a trick. I am redirecting the output to cat. Remember, cat used to be to show the contents of a file, and now I'm using cat without any file and trying to put the output into a file. And I got stuck. So all that you have to do is to write something. At the very end, when you end complete doing this, you hit Control D. What is Control D? Control what? Control D. D. And you get the content into that file. This is neat, but it's not substitute for a text editor by any means. So that's what I showed you here. So this symbol here is, you will not see this, but this is what you have to hit. Control D, Control and D at the same time. Actually, Control first, D after. Okay, another commands, date. I'll show you this, date. And if you want to see the manual for that, manual date. So commands usually offer arguments, and those are. This command is complex, so they have a lot of ways of showing you different different formats for output. The dates, it can count days, things like that. So that. Okay. So right now, ls has, well, I am being executing this couple of things. So I have 3 files, 3 visible files. Of course, I have a little bit more than that. I have, so all those files that start by dot are hidden. So you can create files with starting with dot. Nothing prevents you from doing that. So it's okay, but those files, you typically don't see them. Another thing is that on Windows, you used to have that's this idea of drives that start with C, drive C, D, E for the CDs, if you still have those kind of things. This kind of structure doesn't exist in Unix environments. It's very different. This follows a tree, and the tree, well, let's start with this one. PWD. This command shows you where exactly you are in a folder set, in the tree of folders that a Unix environment is made of, the file system is made of. They have a very different schema of putting the files and folders compared to Windows. And it's similar to Mac OS, but it still is quite different. The Mac comes from BSD heritage. It's similar to Unix Linux, but the point of divergence is quite behind. So the first folder is this. And CD, I'm using this to explain you another command here. CD change directory. CD. And CD slash put me in the very first directory on the whole structure. So everything starts from here. ls, and I see a few folders around here. Most of those folders are for the system, for the computer to work. And these kind of computers are meant to be used for many people. So we don't want someone intentionally or unintentionally messing with the whole thing. So in most cases, you cannot change the files. In some instances, you cannot even see those files. Your privilege as user doesn't allow you to see those files or to access certain portions of the file system. So in our cluster, there is a folder, and again, we will use the command cd users. cd slash space slash users. Hit enter, and you will see that my prompt have changed a little bit. It showed me that I'm in users. ls, and you see a lot of usernames. Every single individual has a folder, 10 gigabytes quota on a personal location. Another command, another trick. cd space, and you start hitting TRA, and you start hitting the tab. Right now, you just write that cd space track, and you hit tab, the tabulator. The tabulator on top of the caps lock, the tabulator, and I will complete the commands up to the point where you get an ambiguity. So it will show you, well, what is that? What is that? Oh yeah. So I was here, users, and we hit the tab. It completes me up to training, and I can hit enter. So I'm now in training. I can see where I'm now, PWD. So I am playing with two commands here, showing you the structure of file system, the tree structure of file system, and two commands, cd and PW. cd, change me the directory, PW, tell me where I am. I am in training. I can see what And we have 149 training accounts. I don't know how many active, but we see those folders. Okay, my folder is training 001. Try to go to your own folder, training 001. Let's check that I'm the right place. If you got lost at some point, meshing with our, you just hit CD and enter, and they always send you back to your own home, your own folder. So you can explore. If you cannot see something for any reason, for security, you will not be able to see it. For most part, the system is secured, so you cannot harm the system unintentionally. Let's say trying to delete files, no, will not allow you to do that, or try to watch other people's data. You will not be able to see that. You will not be able to see critical data or things like that. So you can explore. If you cannot see something, it's okay. You don't have access to that. But don't feel that you are restrained. Let's say you are able to explore. Let me see what else I may have here. Okay. Crash. Okay, this one. Now let's make folders. This command allows you to create folders. You should start organizing your data when you start doing your research. Try to organize in the very early stage of your research how things will be encapsulated. Either because you are working in 3 papers, so you have one folder, paper 1, paper 2, paper 3, or something like that. Or you have some data here, and I have my scripts here, and I have my output here. The order is up to you, but try to be organized. And this, very quickly, when you start doing a scripting, you will start creating a lot of data, and very quickly you will not be able to manage that if you are not organized. Folder 1. Notice that I'm on purpose and either not adding spaces or prefer to put underscores instead of spaces. Because otherwise, if I execute this, I am doing something entirely different. If I execute this command, you will see that I'm executing and creating 2 folders. One is called folder, and another one is called 1. So that's why I create the folders like this, nkdir folder 1 or nkdir folder underscore 1. But doing this will not create a folder with a space. There are ways to do it, but again, it's not the best. You have to encapsulate that in quotes, double quotes or single quotes. For this purpose, doesn't matter. Or you have to escape it this way. Folder, let's say, like that. This way you have one folder that is called folders. And if you want to do anything with that, you have to use either quotes or escapes, escaping the space with the backslash in front of it in order to manipulate files with the spaces. So usually it's a pain, so you don't you don't do that. But from time to time, you receive those folders from a graphic user interface when you create those because it's nice. So you have to use those quotes in order to manipulate them efficiently. So let me see what else we have here. So that's why when I'm showing you this, I always put the underscore. So let me go to this one. So again, now let me CD F, I execute tab, and it go up to folders. I can execute tab again, and it show me all the possibilities that I have, all the folders or things that I can use that start with folder. So just folder, or folder 1, or folder space 1, or folder underscore 1, or folder space 2. If I want to go to this one, I just complete, hit tab, and complete. So I try to avoid typing as much as I can. I always use tabulator to complete all the files, commands, all that I need. Is efficiency. You don't want to do this all the time. So, and I can change the command. And there is, so right now I'm here. Okay, pwd, show me where I am. And I want to go one folder up. So you can see or down, it depends. So imagine that a slash is at the very top. It depends how you call it, but anyway. So I want to go to the previous folder, the folder that was up to this. 2 dots. So CD space 2 dots. And the 2 dots must to be together. But the name, the amount of space here doesn't matter. And I move one folder up. So that's okay. Oh, yeah. So just to show you that you cannot screw things, let me go here to a slash, and let me try to create my folder. So I first execute CD slash, send me back to what is called the root folder. So that's why the idea of this being at the top is not actually the best metaphor, but anyway. And I'm trying to create a folder right there. I will tell you, no, you don't have permission to do that. That folder, I don't have privilege to create folders on the very root of that. I can do it only when there are a few places, but typically where you want to create folders, files, whatever are your home folder. If you have a real account, not a training account, and by the way, for those of you who will attend the next one and the next one, every week you will get different training accounts. So whatever you are doing here will be lost for the next week. So don't assume that for the next week for the Python or for the next week for the machine learning, you will be getting the same thing. So if you want to save your stuff or do it at the very end of this workshop, you will get a new account for the next one. So you see that you want to create this. If you have a real account, you have this Scratch folder where you are not constrained by the 10 GB limit. So you can create terabytes of data. Nobody will complain. A few terabytes of data is okay, not hundreds of terabytes. Yeah, at that point, yeah, you will be in the top 5 and yeah, you will be searched. Let me see what else we can do here. Okay. So here I'm showing you how to create folders with spaces. Another way to create folder with spaces with escape. This, as I show you, will create actually 4 folders. Another folder with spaces. Those 4 folders. You will see those here. And again, ls minus L will show you all the folders that we have right now. There is this command. I will move here without quickly because you will have some time to actually create a few folders and play with them. There is, let me see, that I would like to delete this folder and here. One. I can delete empty folders. If the folder contains something, I cannot delete it. I have to delete the contents of that folder before I delete the folder itself. Or I can use another command that will delete recursively, but I will show you that in okay. Now a few commands to copy. And I did it with this. I said, okay. So I execute this, and I can create 2 folders, odd and even. So let's see. I have here a folder that is called even. I have here a folder that is called odd. Or if you see this way, this is a folder, this is a folder. On these kind of systems, it's very easy to know when something is a folder or is a file. But if by chance you are on a terminal that is not able to display colors, you will not be able to differentiate those. And as I told you, in Unix, in Linux, those extensions are completely optional. So the fact that something has no extension doesn't mean that it's a folder, or something that has an extension doesn't mean that it's a file. All that you can see is this D at the very beginning of this command ls minus L. If it's a D, you know that it's a folder, directory. If it's with a dash or something else, it's not a folder. Typically, a dash is a file. Yeah.
At the top, can you explain why it's showing total 0 after you do ls
Total
minus L?
0. I don't know. I don't know what is the meaning of that. I have no idea. Good question. Probably will take me a while to figure it out what it means. I have no idea. I will tell you later. What is the meaning of this total 0? No. Size. I don't. I will search for that during the break, and I will tell you. I never paid attention to that. Okay. And this is a very cheap way of creating files. Touch. So you put touch a number of files, 1 or more, and it's basically creating all those folders, empty files for you. So you see, I create those folders. I need files quickly, and I use this command to get those files quickly, to play with them. So touch will do that. If I execute it again, the effect is slightly different because the file exists. It basically sets the modification time for that file to now. So, and then I have some usage, but I will not go into that right now. So I create a few folders here, just to show you how to copy and paste, copy and move folder files into folders. So I will move MV 01, F03, and then 05, and then 07 into what? So I'm moving all those files into the folder that I mentioned at the very end. I got nothing, it means it's okay. And I will move to, and see that I can move here with the arrows to 4. I don't have 4. Okay. 2 even. Okay. I have 11. Okay. This is what. Okay. So MV allow me to move files. Let me see if I touch F3. And I can complete the even numbers. So I can copy a file. Of course, this file contains nothing, but if the file contains something, it's a replica of the contents of that file as F4, 6, go up with the arrow, A, and I create copies of that. And I will move them, 0, 4, 0, 6, 0, 8, to even. Let's see, 0, 3, 2. So we have learned here how to, well, this is what I did for this training database. So you can complete the folders, the files that are missing with CP. This is what I did here with CP, creating copies. And at some point here, I start moving those. Well, this is the fancy way, but I was moving one by one.
Did you need the backslash after even?
No, it's because I hit tab, and it by itself it put me the backslash, but the backslash is not important. It will, if this or the command above is exactly the same thing for this kind of command. There is one command that I know where this slash changes for transferring files. That makes a difference. But for this command, for most commands, the slash makes no difference at all. Okay, so just for you to see if you want to do in the fancy way, there is one way of sending files by indicating all the possible combinations of files that start with 0 and 1 and end up with these numbers, go to odd, and those files that start with 0 or 1 and end up with this 0 to whatever, go to it. This is the fancy way. Just for you to know, we will not go into that. If you just want to do it as I did, is like this. So I'm moving all the 01, the 03, 05, 07, 9, 11 into what? 2, 4, 6, 8, 10 into it. Delete files. We are close, close to the exercise. Okay. So I can, as I told you, I cannot delete this. You try, you can try. I cannot delete it. I cannot delete it because the folder auth is not empty. And this command rmdir is only able to delete folders that are actually empty. I can delete files. Let me go to this auth. And the command to delete files is rm, remove, F11. And you can delete files. Okay? And I can do this. Let me see. Imagine that I'm here. And I have this ls auth. So I have those files. In auth, ls auth, I have those 4 files, and I can delete all of them. Auth star. The star is like a jack. I don't know how you call it. How you call it that in cards? Those that. Oh, I don't know. Well, that means a star means anything. So all the files that are there will be deleted. Okay. I have nothing now in auth, and indeed auth will succeed. So let's go back. I cannot delete here. I couldn't delete it. RMD auth because the folder was not empty. What I did was to delete everything inside auth, all those files inside auth before deleting the folder itself. This is one way of doing this. Another way of doing this is, again, even. I cannot delete even because it has some content on it. But this command that is used for deleting files with this argument R will allow me to delete recursively all the contents of even. If this even contains subfolders, it will try to delete all those subfolders. If that contains more subfolders, it will try to delete those and those. It will go recursively into all the tree beyond that, trying to delete everything, and at the very end, delete that. Okay? This is what I did here. Okay, so before I offer you the challenge and some time for exploring this, these are the commands that we were discussing during this hour. So try to arrange your way to have them around for the time being. I know it's hard right now because you learn the first one, and I mentioned in the next one, and I mentioned in the next one, it will accumulate. Try to take advantage of the mnemonics of this. This is remove, this is move, this is copy. This is my way of creating files, empty files, like touching the file, so it's like creating it. This is create yours, this change directory, this, I don't know what this is. Working directory. Bring working directory, probably that's the meaning of that. The working directory, my current directory, the date, cat, and echo. So I select a few commands and a few examples of that. And this is the challenge. It's something simple that will allow you to do it without me actually doing it. It will ask you to create some folders, some files, to see the file. So follow that. Let's say we give this 10 minutes. Yeah, until 11:30. Yeah. Yeah, not bad. 11:30. Yeah, you have 10 minutes, but try to do it. And we are actually very good in this country. And take this time to ask me questions about these commands. So if you see, let's go back here. And I found this Linux commands, I found this guide, Pocket Guide. Basically, I covered all those commands on the first column here. If you want to download this for you, and except the last 2 or 3, I basically show you the first column. And we show you at the very beginning how to connect to the cluster with SSH. There are a few commands that are most for system administrators, so I will not mention those. So take your time.
It's made also 2 files, not folders, the second part.
Where?
Second sentence, made also 2 gaps. I think that it should be 2 files.
Let me see.
He's creating.
Now, the first part is create 2 folders, and this is a folder.
No, that's okay. I think the second sentence.
Yeah, so on those 2 folders, files, date 1, create also on those 2 folders,
Okay, I understand.
files date 1 and date 2.
I got it.
Yeah.
But by the way, that total number is the size that's in the folder. How much size the contents of the folder are taking up?
In which units? Because appears 0.
I think It changes depending on how much you have.
Let me see,
I
let me
did it
see.
on my
I will,
main account and I
let me
did it
see.
on my personal account and it changed.
Okay, I will execute a
If you
tricky
do,
command.
if you do minus LH, it puts megabytes or kilobytes or whatever at the end of it. So it's more readable that way.
Okay, let me do this. This is a tricky. It's a trick of files and big count. So basically, I'm creating with this command. This is kind of advanced thing, but it's not super important. What I'm doing here is creating a binary file. This is not a text file, but this is a binary file that is basically a bunch of zeros. That's true. 1 megabyte of zeros, actually. So this, yeah, you're right. Yeah, right. So with this, so I create this by big 1 megabyte of zeros. So this is in kilobytes. So that's why it was originally 0, because I have so little things. So basically a lot of empty files. So I got 0. But now that I fill this with zeros, I got. So I can create another file. This is another way of creating files for random. In this time with this command. This command, by the way, is pretty much the same command that you can use if you have the privilege to do that, to erase a hard drive. If you do it in the right way, you can get a military grade erasing of hard drives. You create several random passes of 3, I think it's 3 passes of random numbers. On top of that, you can get military grade erasing of hard drives. So I'm creating something like a slightly bigger. So I'm creating a file with random bytes, no text. This is not something that you can see. It's just bytes. And now the amount that I see here is different. So yeah, you're right. So I create these files, and I can create this tiny version, let's say, not so big. So this one here is 100 kilobytes of data. Again, you cannot see this. The best that you can do is to actually using an hexadecimal visualizer, if you want, to see the contents of the file. Let me see if I can show you this. Yeah, this is the content of it. And this is the hexadecimal of that thing. And this is the equivalent of that if trying to make a conversion of this code, these bytes, into actual ASCII characters. But as you see, there is no pattern in there. Compared with this, let me see, hello.txt, where you can see that those bytes, those hexadecimal, those bytes, have an equivalent ASCII character, so they make sense. So they are actually a text file. So there is one character that is 1 byte that is equivalent to the H. There is one character that is equivalent to the E, the L. This is H, A, L, L. This is O. This is the character for the space. This is W. So each character has an associated byte. So this is a text file, and you can see that. And again, there is a character associated to new line. That is like this one. No, it's this one. Okay. So yeah, that answers the question about what is the meaning of that total. It's in kilobytes. So at that moment we have nothing. There is another command. Just you want to see the size of whatever you have in your folder is du. And it will show you the amount of space that your folders are taking. You can use it with -s, and you see the amount of space in kilobytes that your folder is taking. This is just next command. So yeah, we are in time. You did it. You succeeded with this. It's relatively easy to create those folders. At least a little bit of exposure to that. Okay. So now let's go back. Let's go to text editors. In high performance computing, a lot of time you will be editing small scripts when you start learning about that, or probably you are using with another program and you need to fill some parameters for the execution of the program. For example, people in genomics could declare some files to what exactly they want to do in their pipelines. People in physics have equivalently some files that they build for executions, for simulations, things like that. You have also the submission scripts where you indicate which are the resources that you want to use from the cluster. And so, yeah, you need to edit files. And probably you have little exposure to what it's actually a text editor. Most of the time, you probably edit documents, not document processor. It's a completely different thing. This is just for editing text files, not formatting, not fonts, not alignments of any kind. No, just text files. And in Linux, I am offering you basically 3 options right now. Progressing in order of difficulty. So you please have the time right now to see the 3 of them. Try to balance your feeling about which one you will like to use. The choice is very personal. So the first one is Nano. It's very easy, very simple to use. Well, see if I can show you editing a file, say with Nano. Nano. You see? So I can move here with the arrow keys, and I can go here and change this for planet. Super simple. Move up, down, change. Would like to exit, and they put me on the bottom. This the commands that I want to use for several purposes. I want to exit, for example. They say that it's control. So actually, key control is not that symbol, but actually the key control, Control X, and it told me, okay, if you modify that file, do you want to say that? Yes, no, yes. The file will be this, yes, no. Enter, enter. Super simple. This is the first editor. So you can see, and you have, if you want, you can use those F keys to accelerate the operations. They have a few more commands that you want to use. So if you want something simple, you don't want to complicate your life with learning a complex editor, use this one, it's okay. Emacs. Emacs is a much powerful text editor. You can do a lot of things with this. You can even write emails and do fancy stuff with this. Emacs. Emacs works like this. Same thing. Emacs. Hello. Oh, okay. If you do it on a graphic environment like this, it will pop me, create a window. So we'll export because I have this exported. If you are using POTI, it will execute. It will work like this. Exactly if I do it. The text editor on a terminal, not popping window. So I can again move up and down. I can delete. But you need to know the commands to edit, exit, search. For example, you want to search planet. So Control S, and it will search the word for me and put me on top of that. I can, to exit, I need to Control XS, Control XC. So you have to exercise your chords properly to do it right. So this one needs a little bit more extra, you know, with your fingers, basically. Everything is with control something, you operate with that, and they will not tell you below what exactly you have to type. So this is one reference card. This is the official one that say, again, this is something that you can download. Search for this one on Google and you will find it. They have 2 pages of this. It's 2 pages with all the commands that you can use for editing files. And there is VI. VI has the advantage that on every single Unix system that is POSIX compatible, so basically any machine that is Unix, Linux, BSD, whatever, will have VI somehow. Emacs, not for sure.
Can you go over how to get out of the editor?
Yeah, this is something important. So an Emacs, the way to get out of Emacs is Control X S to save, if you want to save something, and Control X C. So what I execute was Control, let me see. Probably I can show you exactly where that is. In the this one. Here, right here, to exit. Control X. I actually never raise my hand from the control, so I push Control. So I keep that chord, and I put X, and after C, and raise my hand. Very simple. If you practice piano before, this is it. Okay. And there is VI. VI is different. Again, this is an editor that has been around for many years, but probably more than 40. Okay. And is the replacement of an editor that you don't want to use. So you will not go below this, VI. It works differently. And VI, hello. Actually, I'm using this version of VI. Vim, there's the VI improvement. Just because I can show you things. So if you try with VI and you start writing, at the very beginning it will not work. The only way you can start editing files is when after you hit the I and you see this insert here and you edit, you file. You want to leave from the exit mode. So the VI works in modes. They have several modes. So they have the insert mode, they have the command mode, that is, let's say, the default mode, and they have the visual mode, probably demo. So this is the command mode. In the command mode, you see nothing here. And by the way, when you get scared of this, because at the very beginning this is scary, you hit S, you hit column, and you hit Q, and exclamation. So those things that you see there, and you leave. This is probably the most scariest text editor around, but it's very powerful. You can do a lot of things with this once you know it. You want to search for something, you put a slash, and it will search for that. I can get into insert mode and edit. I can go to a specific line in the text. So escape 2 dots. Let's say I want to the line 8. Will be exactly to the line number 8. This is very, very common when you are a developer, when you are a programmer, and something fails, and the source code will tell you, okay, in the line 2500 something, you have an error. So you don't want to scroll down tens of pages just to get to that line. You just execute this, go to the line that you know that there is an error, and you fix the issue, and you continue. So this is a very powerful editor. By the way, there is something else. They have this, for example. You can go into visual mode and copy or select. This is just selection, and copy. Copy is Y. It's called yup with Y. Okay. We'll probably not see easily the result of that, but let's see if I can make a space here. And I want to paste. You have to be in command mode and hit P, and you paste those lines. You want to delete one line, delete it. So I found this one. For me, it's beautiful. This is very well done from the graphics point of view. With all the commands, how you move around with VI, up and down. And the nice thing, well, the history about this is that VI was created for a time when terminals were extremely slow. You usually connect for something that young people probably never heard about, those modems that actually do some crashing sound. Well, if you're old enough, you know about what I'm talking about. if that differentiate from which generation you are. If this is a completely out of this world sound, it's because you are too young. But if you know what a modem is, okay, you are accumulating some years, if you like. So for those times, and these kind of keyboards, what I'm showing you here, these were the keyboards of those times. You see no arrow keys. So you have to move around playing with this, with H, J, K, L, M. And that's why those are the keys that you use in command mode to move around when you don't have an arrow keys to move around for you. And I wrote a little bit, the post here, a little bit this story about how the guys create this, why they did it, why BI was like this. And if you want, use this one as an example. And I have a challenge for you. So I will give you some time. I will try to adjust the timing for this. The challenge is to write this code. For example, in VI, if you feel scared, just do it in Nano or something. If you feel the spirit of adventure of this, do it with VI without using the arrow keys, not a single time. So just moving around with the commands and going with this. It's not too big, but it will take you a few minutes to complete this. If you want the bonus points, use the copy and paste to copy in this and paste it 2 times here and here, and edit the extra 4 loops on this command. Once you have written this, check that it's right. It's a very tiny piece of code, but everything has to be exactly as it's written. So, for example, here there are 2 spaces. In order to this to work for the kind of thing that you will see later, this has to be with 2 spaces. What else important? Those quotes need to be like this. This symbol, this have to be like this. And this semicolon is extremely important because this is C code. So in C code, these semicolons are extremely important. And write this file with this name. Once you have done that, execute this command on the computer to compile this code. Once you have compiled the code, execute, and you will see something nice. So you will see the reward or the reward of the effort of doing this. I don't expect you do this on a daily basis. It's just for you to get the feeling of the command line, on looking at those commands, familiarizing with moving up and down, copy and paste, open the file, editing. If you don't want to feel the pain and you want to get this in 5 minutes, use Nano. Use Nano, it's okay, I don't care. It's up to you. Or use Emacs if you want. It's okay. Use whatever you want, but the challenge is with that. And I will give you some time, so that's why. And if you want to ask me questions about those editors, I will try to help you. Most of the time, it depends. I use both. I never use Nano, that personal. Most of the time, I use Emacs or I use VI. It depends on which kind of files I'm editing. And I use one or another. Or because simply I know for sure that VI is everywhere, so I use VI. But
Is that a graph?
well, there is this. So if you use Emacs and you are in the mobile store, So you get a graphic environment. So you can create a file, and it will pop up something like this, and you can edit the file. So you can move around, and you can save it here. You can have some options here. In that case, when I use in a graphic and I am doing coding, I'm writing Fortran, C, or those languages, I use this parent matching to get an indication where I am opening parentheses and closing parentheses, open brackets, closing brackets, these kind of things. I save these options. I usually work with several files at the same time, because if you are working with a code that has 1 million lines, you probably have to edit in several files at the same time to get the job done. So at that moment, probably yes, this one I use more often in that case. Also, I like the way they color the syntax for some languages. So for big things, I tend to use more Emacs. For the small files, for the small configuration files, I use VI quickly, and I do. So I feel comfortable on both. And at the end, if you get deep into this, probably you want to use VI, you want to learn VI. If you are just starting this, you probably Emacs will scare you even. So use Nano, because all that you need is to edit a file. So that gets the job done, period. And with time, moving to Emacs, at least Emacs is okay. And if you want to use the graphic environment, it's okay. So, okay. So take your time.
Can you go back to the instruction page there?
Oh, sure, yeah. For which one?
For the external that
For the what?
the external universe.
Oh, yeah, sure. Yeah, sure. Okay, let me see. If you want to use something like this, you can print it. They have a nice thing.
Yep.
Okay, so let me explore a little bit the kind of things that probably you will use when you face it. If you try to do this, you start writing. as you are learning this and you make mistakes, the first thing that you know is how to undo this mistake quickly so you don't screw the whole thing. You go to escape, column, and it will go back for the last things that you have done. It's not the last line, but the last few commands, or the last text that you have entered. So here, when you see nothing, you are in command mode. When you hit I, you are in insert mode. When you escape, you go back to command mode. So command mode is the first thing, is the main thing. You always go back to command mode. You go I with insert. You escape with command mode. You go back to visual with V, and you go to visual mode. In visual mode, you actually are selecting the sections. So you can delete those sections with D. Actually, this D is actually storing that information with P. You can paste. So that's the kind of thing that if you want to do this with a bonus point, with a for loop, you want to eventually use the visual mode to select the for, copy that, go to command mode, move a couple of lines, one line, paste, go another line, paste, and change the small details in those for loops. And that. There is another thing that this is nice. This is useful actually. This is really useful. If you are imagine that you are editing columns of files, this is really useful. This is a nice trick. And you want to, you have imagined that you have something, it's nicely formatted, but they have several columns and you want to delete one column or do something with them. You can enter with this Control V, enter in a special mode that is called Visual Block. And you can select the block and eventually delete that block. This is hard to do with any editor. And it's a nice trick, especially actually in research. You have managing columns and you want to edit. There are better ways to do that if it's for an entire column with the grep or awk. I will show you that for the last session for the shell. But the block, the visual block is really useful.
How is the visual block? Control V.
Control V. From the command mode, Control V, you select the one corner, go to the next corner, it will be, and you can delete to delete, or you can copy with Y, and you go to another place and you paste it, and you place the block. So let me see if I can do something. Control V, and I paste that. And I paste it here. I paste it here. Oh, I screwed this. Like this. So you see that I insert this column, so hello, one after another. You can do the same thing with image. I don't exactly remember exactly why, but it is in the documentation. Let's see. Oh yeah, the equivalent for that in Emacs is right here in rectangles. So with Emacs you can do it exactly the same. It's works slightly different, but it's the same idea. You select, you create a rectangle, you copy and paste that. I don't think that you can do that with Nano. So those are complex operations that Nano will not allow you to do. I'm not 100% sure. Not.
Classes.
How is this up to now? Too hard? Too easy? How many of you have experience with Unix before, with Linux? You? Okay. The best. At least on Spruce, we have Emacs on the head node, so you don't have to worry about that. I think we don't have Emacs on the compute nodes. So, do we have Emacs on the compute nodes? No. Okay. So if you are doing interactive computing, you need to know a little bit of BI. If you plan to edit files, if you just plan to use any other program or MATLAB or whatever other thing, probably you don't care. But if you need to edit files, you need to learn.
They have access to those GitHub pages to be the stages you're going through.
Yeah. The what?
The GitHub pages.
None of them.
Yeah.
So, yeah, I show you here. Okay. So if you go, you want to see this, you can use this, or you can take a photo with your cell phone if you have a QR. and you want to see the pages on your cell phone so you can scroll the commands or whatever. So I did it on purpose so you can get another screen for your own.
Which one did it? Was it?
What's the problem?
Yeah.
Yeah, that's.
I put it in the chat, but not in the chat. So. Don't forget about lunch.
That's exactly what you're.
Yeah.
I don't know why that would work.
Okay, so let's do something. Let's do something. I will show you just a little bit of advanced thing. We are. We're actually very good on the schedule because I am allowing you to work on this. And we will return at 2 o'clock. So you have some time to spend. I will just show you a little bit. You don't need to learn this if you don't want. This is kind of advanced. Now if you feel comfortable with commands and terminals and things like this, there is just one more thing that help you work for this for real. It's TMUX.
Yeah.
With TMUX, what you do, and again, this is advanced, it's too complicated, don't worry about this. I'm saying anything. This basically creates a virtual terminals, several virtual terminals, where you can work on them from one simple actual terminal. So for power users, for real HPC usage, this is a good thing. And another thing that it has is that once you have this, it preserves the status. So you can work on here on your computer, close, go to your home, open, continue. Otherwise, you have to go back to the folder where you were working, come up and reopen the file and things like that. So how this works, again, this is advanced. This is too advanced. I'm just using the time for you to write this code. I know it's 5 lines, 10 lines. It took me almost 10 minutes to do it, and I am relatively comfortable, but I'm not used to I used to do it with the keyboard, or arrow keys. So he will do it in 5 minutes. He used this VI with the old style thing, but no. So TMUX works like this. You execute this, and you get a new terminal. There are several ideas here. You have terminal, you have session, this is a session, and you can create windows. The way you create windows, the magic key is Control-B for everything. So I have right now one session, and that session has one window, that is the 0, and one pane. I can create another window with Control-B, C. B and C. Control-B, C. And you will see 0 and 1. And you can jump into 0 and 1, Control-B, 0, go back to 0, Control-B, 1, go back to 1. Control-B, C. So, this is Control-B, y después, after that, C. That's how you create a new, yeah, okay. Control-B, no, the uppercase doesn't matter. So you can create panes. You can split this window into panels of panes or whatever. Control-B and double quotes. The double quote. So something like this, Control-B and this. the double quote, and it splits that two places. You jump into, cycle into those panes with Control B O. Control B O is you jump. You want to see the date, Control B T, and it will show you the date, the time. So you can keep one. So this is a little bit advanced. Forget, otherwise you can still writing your code is much better for you. We don't need this. We don't need this. We will be working on a single terminal the whole session. I'm just trying to offer you Control B O, and you jump. Look, so here I'm here. Control B O, and I'm jumping here.
Probably 0, right?
Huh?
Say 0.
No, Control B O. Letter O.
You don't have.
Control B O.
You don't have another tab. So
Do you?
Control B1. So you're at lunch.
Yes, yes. If you want to, you don't want it here. Go for lunch. We'll come back at 2 o'clock. Yes. Control B D. Control B D.
We'll break for lunch. We'll probably right now start back up at 1:15.
You want? We are ahead of time because I set up too much time for the editors.
We'll give them a whole hour, then
Yeah.
back at 1:15, and then they can go home early if we get that.
Okay.
Sure, no one will complain about that.
Yeah.
If you want to stay here for lunch in the room, feel free to do so. There's a break room down the hall here where you're welcome to go out. You're going to go out and come back and use your ticket. Just make sure you see me to get it or me or name. Has everybody already got a parking ticket? If you want, just go back there and see Daniel. If I'll help you. Anybody else have questions in the room? If anybody have questions online, you're going to with us when we check those throughout lunch.
And the people sign for this piece of paper?
It's back here.
Okay.
Make sure you sign in too if you have it. All you do is put your name, check your name. No, you're good.
I just started seconds ago.
So I continue talking a little bit before you. You reattach the session. If you want to reattach the session, and you continue. Control Tmux, Control B. So this is detaching the session. So everything stays as it is. So you can go home, or you can go to another computer and continue working. Control B. So I will put it like this: Control B and D. Lowercase d. There is a difference between lowercase d and uppercase d. So Control B. So actually, it's like this: Control B, D. So this is the way of you detach, and you reattach with Tmux A. I use this a lot because I'm working on, I have several computers. I have my desktop computer, I have my this one, I have another computer at home, and with this I preserve my status, I preserve my environment. I have several windows connected to different computers, monitoring different things. Let me go back to this one. I can create a vertical tab, so split and vertical. Control B percentage. So what I did here was Control B percentage. Everything is Control B something. You can jump into different, I can create more windows, more sessions. I can, for example, have something executing here. I jump into Control B0 to go to the first one, Control B1, Control and this is a very popular terminal multiplexer. So for sure there is one reference card like this, where you can see all those commands and the different ideas with that. You have sessions, you have windows, you have panes. You can create new panes, new windows, new sessions, and you can jump between them.
Yeah, we'll do that. We'll only do it one time.
You go start, tell me, I will help you.
How do you get back down for ourselves?
What?
How do you get back down on the screws?
Yeah. I think you get generally the gist of what he was trying to show you.
If you see here, here, the docs, HPC, WVU, this is our official documentation. There is one quick start, getting access, and they have exactly what you have to do. It's basically create a ticket, and you ask for an account, and you will get a permanent account on our class. You have to provide an abstract. Now it's not that we approve or disapprove your project, whatever. You will get it anyway. Is that you have to write like the kind of abstract for a journal, where you explain what you are using the cluster for, and you will just basically paste that into the NSF reports for justifying how you use the money for that. So it's not to prevent users to actually get access.
And you have a PI, like your teacher who you're working with.
I don't.
You listen.
So I don't know what it
PI,
shows you.
that don't actually really know them.
So I don't know what terminal were you? What editor were you starting?
I show you Nano, Emacs, VI.
Nano is actually the easiest.
And Nano is the easiest. If you are never used to do this before, Nano is the easiest.
So what I would do if I was starting out is BIM is good. Right, want to learn it, but don't start. BIM is kind of.
That was my final
So if you
result.
go
I
with that,
copy pasted that.
Maybe you have a mistake. You have a bug in somewhere in the code.
You don't have to use it.
Let's check. Let's go. Yeah.
You show you have to
And let's compare with the code.
You want the code?
Yeah.
Your original writing?
Yeah. Okay.
They're good. 7:15. And we'll be in here. Then we'll be here going.
So the original one, this, I did this first. I got the tree.
Oh, you got the three?
Yeah.
The triangle. The triangle.
Yeah.
You got the triangle. Okay.
Yeah. And then, then I replaced that line
There's also a little.
and that line with this line, which is the same as the first line.
Yeah, it should be. No, it should. No, the idea is that the idea is that you copy this and you edit those.
Yes.
to
More likely.
match. You know what I mean? So the idea is that you have been copying this, but now you have to edit this file, this line, right? So you're supposed to write something like
I don't think it does.
I equal to 0. You know what I mean?
I don't know.
That's what I originally had.
Yeah, this is the challenge is not having to write the line entirely, but just copy paste 2 times and edit.
Okay.
That's what that is the trick.
Okay.
But if you got it, if
Yeah,
you got it writing the whole line, it's okay. You got the 3. And,
Oh,
so and then there is. So you did it, right?
Yeah.
So I can delete this.
Yeah.
Right. And so let me see. And so there is a one-way pasting. So escape to those set paste. And this, and I will copy and paste this small code. See? So it's just a code.
I'm gonna pause your recording.
Okay.
Sorry.
And you should get this, the fractal.
Okay. Okay. Thanks.
Okay. It's not that.
We're gonna start back up, and then if you needed parking, you left and came back. Just make sure you sit in the back.
Okay. Let's continue. For the kind of things that we will start doing now, it's time for you to download the codes and small pieces of text that are prepared for you to explore the kind of things that we will be doing. So copy this and execute that command on your terminal. So I did this. Let me see. Let me show you what happens. I will delete first. So this is.
Make sure you talk loud so people can hear you.
Yes. So I want you to execute this command. Let's see.
It is
Maybe right here. That can. It's exactly the same as within.
You have the
Okay. So it's here, you go here, and you can copy from the setup here. So this is the main page of our lesson. Right here, setup. This is the command that I want you to execute on the terminal. So it basically will download a few pieces of code, some files, some elements that will allow us to explore the kind of things that we will discuss today and tomorrow. So when you execute this is what will happen. We'll connect to a repository, we'll download all stuff. And if you execute ls, you will see a new folder populated that is called 2019 data hands-on. Let's go to that. Go to intro HPC. And for example, if you go here, editors, you will see the solution of the challenge or the actual source code. If you didn't have time to go the whole way into editing the file, I will show you what it does. So I will not, this is not the moment to understand what exactly it is, but this is the command that I give you to compile it to execute. So once you get this and you execute the code, you get this. This is a fractal. This is a known fractal called Sierpinski triangle. And this tiny piece of code was basically creating this. So, so we are here, DWD, we are here. And we will.
Excuse me,
Yes.
I'm just in my folder. Do I need to be in editor?
So where are you exactly? Are you in Spruce? Yes.
I'm in Spruce.
Are you in Spruce? You execute the command, right? This command.
Yeah.
Let me see. CD, and you execute this command. This command. So what I did was copy and paste
I have the CRPC.
I copy and paste this, and to give you the solution, to give you the actual code, so you can compile it if you didn't have the time. Or I know for you, if you are not used to those editors, even with Nano, it will take you a lot of time to do it. So I am giving you the answer so you can see what those 10 lines of code produce. Those produce for you. So I copy this here and I execute it on the terminal. We are on the same page because we need all those files on your accounts, so you can follow me when we start entering in the you have it. You have the files. You execute this command, git clone, exactly as it is. If you prefer, you can. I will put it here. Right in the middle. This is the command that I will, as it is.
It's also in your documentation, just copy and paste it.
Yes, copy and paste, or just write. I will wait a couple of minutes for you to copy and paste that exactly as it is. If you get an error, it's because you make a typo somewhere in that line. Otherwise, and please don't execute this twice because all will not accept it because it will create a folder and it will not try to recreate the folder. So if it's good, you have it. You have all the data for today and tomorrow. And I don't want you to have to write those files. It will take too much time to doing that. So I will give you the files so you explore the kind of things that we will mention in the next few episodes. Yes.
What happens when you do execute it twice? How do you?
Let me see what happened. Well, you will see this file destination path already exists. So you have to do, if you are not sure that, or you screw up the thing, just delete it. So I'm delete the whole thing, and I clone the repository again. So is everything fine? If you damage the file, and you don't know, git commands, delete the whole folder and do it again. Then it's okay. You will download the whole thing. Again, it takes a few seconds. Super.
When we are in, do we need to get to the subfolders of this main?
Yes, and now we will have to go into the subfolders to explore what is in there, and I will explain you on each of them is for each episode, for each section of these hours. So I put some pieces of code, and I will explain. Okay, in these modules you will see this, and this is what we can do with this. And after we will meet in the compile, you will see another files, and now you will see another things for tomorrow. All the things that we will be using in the next few days. Again, I keep everything. So there are those web pages. I keep those from the previous year. I keep those for 2017, 2008. So everything is there. I never delete those repositories. I basically, for this year, I took a little bit of the previous year, but most of the material is brand new. Okay, so I imagine that you have this folder, 2019 data hands-on. You should have it. If not, please tell me, because there we have. So CD 2000, and again, I use tab all the time to complete the line, to complete the folder. So if you will go 20 tab, it completes the whole line. So you don't have to write all the time everything. So go there, hit enter. And now ls, let's see what is in there. There is one folder and one file. So the folder is for today, for this workshop, for today and tomorrow actually. CD1, I hit tab, completes, enter. So super, it's much easier if you exercise yourself with executing tab all the time instead of writing the whole line. And you will see some folders in there. ls, a few folders. The folders match what I wrote in the summary, in the lessons that will in the episodes that we will manage today and tomorrow, and they follow the order exactly the same. So I show you editors, and the file that I asked you to create with the editor you preference, so VI with the challenge, is this one. So you see, let's execute cat. With cat, we can see the contents of the file. I hope you can see this file. Try to go to this folder and see this file. This is the code. And see that you get exactly this. Please tell me if you are not able to reach this point online or here. Because we need this for what we will start doing right now. So 05 modules. So if you go to 05 modules, you will see a couple of files. Let's wait, and if you want, just go CD and let's explore what I have to tell you about this. Okay. So, a HPC cluster, as I told you this morning, is a machine. It's an aggregate of computers. It is basically it's like those big, imagine those big refrigerators, 3, 4 of them aligned with 20 computers on a stack, 20, 30 computers. Not like this, but like slabs, kind of the machine that we have here. Those are like slabs that enter one on top of each other. And they are connected with a special network cabling. And many people use those machines at the same time. So actually, how many users do we have, Nate? Like 100, 200? 3 to 400. So it's a machine to be used for our entire community, for our entire university. People in all disciplines with different interests, with different research projects. So we have to support a bunch of different codes on that machine. Some researchers using the same code, but not all of them. So how we manage offering a variety of codes, a variety of software on a single machine for such amount of people. So the solution for that is called environment models. But before I enter in this, I will explain you what a variable is, and later what environment variable is, and how the environment modules solve, which is the problem that they're solving. So I told you that you can execute this. Home is a variable. Actually, it's a very special variable. It's called an environment variable. So it's a variable that you have from the very beginning, since you enter in the system, you log in the terminal into that machine, you get that variable set up for you. So there is another, for example, this one, user. You get your username. There are a collection of them. If you want to see all of them, all those special variables, you execute this command, env. Those are the environment variables. So those special variables that are there for you for executing for the different programs, and yourself execute things with it. And you will see a collection of them. So let's see. This could be tricky. What matters to you probably is, okay, the user, I show you, is training, 001 for me. Forget about this one. This one, for example, show you on which is the language that has been set up for this machine for sending messages. So if you configure the machine for different language, you can see the manual pages in a different language, the messages in a different language. So that's a variable that allows you to change that or manage that. This home variable is what I show you. What else? What else? This one, for example, is showing you from where are you connected. Display is because as I am using this with mobile extern, I have the ability to export my windows that I create back to this computer. So this variable controls that. The scratch, well, that doesn't apply to you, but for training accounts. But anyway, so there are a few variables. Consider that like global variables. They're always there. Programs see those variables, and they can change their behavior based on that. They are different from the normal variables in Shell. Shell is a programming language, so you can create variables on that. So I can create something like this, and this is a variable. I can create something like this, and this is a variable. And I can execute this. It works like this. Oh, yeah. So I can operate with those variables. But those are not environment variables. Program, and I have one example to clarify that. Well, if I create a program, the program will not be able to see this variable and will not be able to see this variable if it's not exported. And the solution for that is to export that variable. At that moment, that variable becomes an environment variable. So it will appear here. Here. So now this is an environment. So this variable has gained a status of a global variable, something that programs can see and can change the operation based on that value. And many programs actually use that for a variety of purposes. But just to show you a few of them, this one is extremely important. What is that? Well, I will show you that one. Again, this is an operating system that is not based on icons. So how you know where are these executables that you want to use? You have to indicate several locations, several folders where programs are located, where programs that you can execute are located. So this variable controls that, where to find programs. So it will, when I execute the program, when I try to execute something, it will try to search first here. If it's not here, it will search here. If it's not there, it will search for this place, in order trying to find a command. So let me see if I have something here. ls, and there is this command that will tell me where it is. Oh, well, okay. If I execute this command, it will tell me exactly in which location that command exists, so I could execute it. And it told me that this command told me, okay, date, the command date, the program is an actual program, lives in this place, /bin. Actually, a lot of those programs that we saw today are right there, /bin. So see, there are a bunch of them. So if you execute ls/bin, enter, you see some recognizable places here. So you will see, for example, cat is here. You will see cp, the copy command, is right here. And the date command, right here. What else should we execute? This amp command, ls is right here. mv, rm, rmd. So those commands, those basic commands, usually are just there, /bin, and they are here in my package. So right here. So this variable controls where to find commands on the system. Let's do something. If check that you have something like this, right? You should have something when you execute echo.pad. You should have something like this. Well, let's do something. This is a small thing, but let's. You see the folder itself doesn't exist, bin. So this is a good exercise to connect this with what we did this morning. Let's create a folder bin. You should know how to create a folder right now. So create a folder bin right on your home folder, go to it with CD, and create a folder called bin. I will do it right now. Okay, let's go into that folder. Okay, right now we have nothing. You can check that nothing is there. Let's create a command for us. Your own command. You will have your own command. So I will do it with what? Let's say BI or BI and grid. I will create this command. It's called grid. Okay. So you can do it with Nano. You can do it with Emacs. If you try to do it with a Nano, if you like, it's easier. You know what? I will do it with Nano. Okay. So now you will start writing this. Don't pay too much attention to exactly this, but I will write it. This is magic. This is some magic. It's not an advanced technology that is indistinguishable from magic, but consider it like magic. It's actually a magic thing. It's called that way, but or Shibanka. Let's make a hello. Hello. My username is just write that. Not just those lines. Let me see. That's all that you have to do. I give you a couple of minutes, so write that. Pay attention to what to this symbol here. This is important. What I am writing is a very silly or minimal shell script that will put some things on my terminal and write this whatever for me. Oh, that's it. And you are here. Okay, I add a couple of things. So try to edit this and let me see, exit this. Yes, try this. Check that I wrote this correctly. So this is the content. Try to mimic this as close as you can. Exactly this. We are creating our own program, our own executable thing for us. Everybody have that complete? You need a few minutes? Okay. In the meantime, we try to see again these variables. So you write this when you want to leave, to save. Remember that it's Control X to exit, to finish, to write that file to your computer. Control X. Well, if you edit something, you see that I will remove this. So Control X, it will show you this message. The buffer, the file, this is called buffer, but I've changed. Do you want to say that those changes? You say yes. The file, the name of the file is read. Want to save it? Yes. Enter, and you get the file. You have okay. What kind of things we have here? If you didn't write this one here, probably will be fine. People will execute with the internal shell, and this has not departure. And the internal shell probably is dash or bash even, so will be okay. But if you start playing with flavors of shell programming, there are several shells, so you need to be specific on which shell actually you are using. This is too generic, so probably you will see any effect. So this couple of things indicate which shell you want to use, and bash. And we'll execute those commands line by line, and that's it. Next thing, so we are here. Everyone is on the same page, right? So now let's do a small change in .file. This is something that I didn't show you before. We will just change the permissions for that file with this command. Before I do that, I will show you exactly what changes. So right now you see this file. Execute this with or without this. If you want to execute this, it's okay. To check that you have the file. The file, if you wrote the file exactly as I wrote it, should be 97 bytes. 97. This is the owner of that file, and this is the group ownership for that file. And this is an indication that this is a file because it has no D in front of it. And those are the permissions for that file. I will not enter in too much details on that, but they control the permissions for owner, for others, for the group, or whatever. But right now, this file, you cannot execute it. It's not a command yet. To make it an executable, we do this. We execute this. Exactly as I wrote. So let me go back. If you want to clean the screen, another nice command, Control L, and we'll clean everything and send you on the top. I want this because I want you to see this clearly. This command right there, and execute it. Enter. Exactly as it. And now do it again, ls-al, and you will see that the file now is green. On your terminals should be now green. And you see this X here, this was not there before. The X. So now this is something that's executable. It's something that you can execute. So you go there and you can execute this. You just write that, and you don't need to be in that folder. And you just write this, and it will execute the command for you. You have created basically your first program in Bash script. Minimal thing. And you were able to do this. You were able to execute this command because this command is located in one. echo in this location. So the shell bash, try here for grid. No, it's not there. Try here. No, it's not there. We're trying every single place until the very end, when it finally found the command that you want. And the command where the file was executable, so it can execute that. No problem. So we can execute this to see where that is. And I will show you this. By the way, this curly thing is a way of compact your home folder. So instead of writing your entire home folder, it writes that. And you can use it. You can, so you can go to curly bin instead of home bin, or instead of writing the whole thing. Users, training 001. All these three things are exactly the same. This one is using an environment variable. So we know now what those variables are. And path is one of them. It's very important where to find executables for some. And there is, let me see, we got some tests. Okay, right now we don't have too much to show here, but at least path is a very important one. If you change by some way that variable, you could be able to access commands that were not accessible to you before. You change that variable for something else, and you will be able to access some other commands. So this is one way to offer different users commands with different versions eventually, with different configurations, different setups for different users. You would like to have that ability on a cluster to allow the users to change their environment at will, to expose, add or remove commands for them when they need it. That's what environmental models are for. So I just show you here a few commands. Right now, the system is so simple that we don't have some of those. In particular, this one and this one are some of the commands that, some of the variables that changes to access different codes for different people. Yes?
So that last, in your tree file,
Yes?
you kept one command per line.
Yes, that's the way they did it, but you don't have to do that.
How do you, because I tried putting like, I go today is colon date, and it just,
Date.
today's date.
Yeah, so because it did, okay, let me see with that. I know. Great. Everything that is here after echo, it interprets like text, not like a command. There is one way of doing this without interpreting like this, is by adding this. A small trick. I didn't want to use it, but it's okay. So you can replace that for this. So basically, it will execute this in what is called a subshell, but doesn't matter. It will execute that. Whatever is the output of that, it will be replaced in that location. So let me see. So now you are getting the date and the location on the same line. That's the only thing. Otherwise, it will interpret PWD as PWD as a word, or date as a simple word. Okay. Another thing to change that. Another thing is that I could do this. Using a variable. Exactly the same thing. So now this time I'm using a variable and storing that variable and storing the output of the command date. And you get exactly the same result. So this time using variable. But this variable is not an environment variable. It only can exist inside this script. Out of this script, today is nothing. It has no existence, no meaning. Okay, let's continue. Okay, so there are some variables, important variables to find executables, but also to find libraries. Libraries are pieces of code that contains the functions, variables and functions that other programs require in order to do their job. And this is the location or where to find libraries when you are executing a code. And this is the location for finding libraries where you are compiling a code. They are very important. They change the way the code operate if you change them. So, environment modules is a nice tool to allow you to change those variables at will with predefined schemas and a good set of dependencies where you can declare, okay, I want to change this, I want to change that. I want to access this code or this other code. Let's see what we have. Again, Spruce is a big machine. We have a lot of packages there. If you execute this command, you will see all the modules that we have available for you to use. Once you get your account, so, you can use it. So let me see, the list is quite big. Let me see, let me point you to the, so I organize this in levels. So all those modules are very basic. Let's say for someone who wants to compile some other things, so where the modules here are related to things that we will mention tomorrow, Conda and Singularity containers. And those modules are for scientific codes. So let's go backwards and see some more, and those are the meta modules that aggregate some other modules just for being easier to use. So if you are in physics, chemistry, and you deal with molecular dynamics, most of those codes here are for that, those in the atomistic section. There is one here for astronomy. Here you see a few codes for computational fluid dynamics. Again, more codes for chemistry, classical molecular dynamics. And this, I don't remember exactly. A bunch of codes for genomics, here and here. Genomics, a lot of codes for genomics. I think this is for finite elements probably, I'm not super sure. Those are more for the statistical modeling, Dakota, this one to MATLAB. It's not exactly statistics, but for traditional has been there. It's more like a general purpose computational environment. Our studio, a few things for visualizing big range of data, ParView, Visit, and BTK. So you see codes for different purposes or different interests. Let's say high-level codes, big codes that have been compiled, optimized for you. And here are libraries, low-level things. So I have pay attention to this one, for example. This is a compiler, GCC, a recent version of the GNU compiler, Java, Python, a few versions of Python, R, the latest version of, well, not the latest, but a recent version of R. What else? What else? A few libraries for numerics in GC, in C++, fast Fourier transforms. Some codes use that thing for storing binary data, large amounts of numbers. This is the standard for that. This is one of the standards for that, HDF5, for large amount of numeric. This is a library for routines, most of them in linear algebra. This is for parallelization, for distributed computing, MPI, parallel computing. More libraries for linear algebra, OpenBLAST, HDF. Here, Julia, a different language. Few compilers. So all those different compilers, libraries, codes, they have modules, and we can switch on, switch off, enable this, disable this, change the version. So imagine that you want to use this version, but you find that this version is not giving you the right result for some reason. So you test another version to see if this version works better, or if there is discrepancies in the versions or something. So it's good to have those things, and then allow you to switch back and forth between them as you need it. Okay, so you need to start getting used to the kind of modules that you need, that you want on your research, and the version that is good for you. I try to keep those updated. I am reordering and match now the kind of modules that we have on the Spruce with the modules that we have on Torney. So this is a transition period, so we are slowly eliminating some of those and match them with Torney Flat, our most recent cluster. So this is one thing. So now the next thing is, what happens if I need to load the module? And I will do some exercise to show you exactly. I will skip this. Let's see. There. Okay. This is another thing. It's important. Spruce. Spruce has been around for how long? 4 years, 5 years? 6 years. Okay. Imagine this machine has been for 6 years in use. So it was installed with Red Hat 6. Red Hat 6 is an operating system for industry, for real critical, mission critical applications. So the most important thing is to having something super stable. That means most of the code is old, or at least very conservatively old, so they can ensure that everything is very stable on that machine. That means that things like compilers are typically very old. So you execute this, and you see that this uses this version of this compiler, the GNU CC, the GCC version 4.47, that appears probably 2010. So it's 9 years old, right? There are codes that are not able to compile in this compiler because they use newer extensions to the language, to C, C++, that were not implemented. No, they were not even discussed at that time when this compiler was around. So that's why you would like to use most poly and more recent compiler. One of them is Lang GCC 8.2. When you execute this and you re-execute the same command that we execute before, you get a different answer. It has changed some environment variables in order to point GCC instead of the Red Hat GCC into the module that I compiled for you with a very recent version of it, of that compiler. So this is 8.2, that was from 2018. So it's a very recent compiler.
Can we make
This
modules for ourselves?
What?
Can we make a module?
You can make modules for yourself. I'm not mentioning that, but this is here. You see the instructions for creating your own repository of modules, so you can create your own packages, your own codes, compile it yourself, and have modules for them, and be alongside with the centrally managed modules. So if you want. You just need to change one environment variable to have a location where those modules are. And those are text files. So I'm not will enter in details on that. I am here on an exercise to propose for this. So, and I start doing this right now for you. So I show you that let's clean the environment first. Before I module purge, no modules. Module purge removes all the modules, give you a pristine environment. The environment that you get when you get into the cluster, and you execute lists, no modules have been loaded. The exercise is to try to figure it out which versions of GCC, Python, and R are right now on the cluster, on this machine. Just executing something like execute for this, minus version, usually that's enough. So you can execute this, you can execute R. No, well, the minus version doesn't work, but if you execute R, you get the version right on top for this language. You know, you can click on this. You can execute Python. And you see the version. So the first part of the exercise is to get an idea of what we have when we don't have any module loaded on the system. With GCC, with compiler for G, Fortran, you have R and Python. Just those three is enough. Try to check that. Now start looking for modules to load, to change that. So one of them I strongly suggest, and this is something that you can do, module avail in Lang. Just to concentrate, show me the modules that are available in the Lang section, in the languages section. So you will see this set of modules. And now I try to explore what happens when you module load this one, how that changed the version of GCC. I try to load this one and see how that changed the version of R that you get. Try also with one of those Python 3.7, 3.6, and check that your Python version have changed. Python 3, there is some special trick here. On module, load, Python 3.7. But if you execute Python, Python minus version, it mentions that it's still 2.6. It's because Python has two versions that they are not compatible to each other. So Python will be still Python, and the Python 3, that is the Python that you're supposed to be using from now on, and is Python 3. So you should be getting you execute this with Python 3. So just do this, explore a little bit what happens when you enable and disable modules. You can module this. I show you the commands on the web page, the commands for enabling and disabling modules on the system. If you got confused on which modules are there and you want to start over from the beginning, module purge. So with just a few commands, you load and load, purge, see what is available. I offered also help on some of those modules. What show what is in there, what the module is about. If you are curious about one module and you don't know exactly what it is, usually I wrote that where I mention, okay, this is this version of Python where I am including a set of scientific packages in there. Sometimes those packages, I optimize them. I not just download them, I compile them myself with Open Blast with some special optimization to give you the best performance that I can on them. And basically the tricks that I use to compile those packages, so you can know how I did this eventually. What is there is another thing.
So if I copy these, I make a module.
No, the module, well, if you want to see what the module is, let's see if I can, I can see. The module is right here. If you want to see one example of a module, it's right here. On the very top, when I execute module show, it put me to the file. It's like this. The module file is this. It's a text file where in TCL, in another language, where basically I describe what it is. This is text that I enter for the user to be able to know what it is, what it has. I preload some modules for the user. I set some variables, and I'm changing some environment variables for them. So I am saying, okay, add this at the very beginning, this location for finding Python. So it will take precedence over everything else. When you load this module. Same for the runtime libraries search path, for the compile time search libraries, for the headers. When you want to compile things associated to that. So this is one example. If you want to see another one, a little bit more, this is a little bit more complex. For GCC, it's like this. So I'm changing a set of environment variables to adapt that and allow the user. For example, this is another thing. Let me see. Let module purge. So GCC minus 4.4. If I execute the manual, I will be looking at the manual for the 4.4 version, right? And if I execute module load length GCC, if I execute the man for GCC, this manual is for the 8.2 version of GCC. You can see, for example, this for example, at that time, in 2010, it was not such a thing like a Skylake processors. So the old GCC doesn't know how to optimize for the most recent models of processors and extensions and all of that. The GCC 8.2 is able to compile for those processors, is able to add those extensions and take advantage of the performance, extra performance that they can offer to you. So that's one reason why I put that. So try to use the newest version of those, if it's possible. Same thing, while you try with the module purge. For Intel compilers, this is the set of compilers that I recommend. I have 2019, but it's not performing, or we are having some issues with 2019. So I consider 2018 update for the most stable and reliable right now. So this is what I recommend people to use if you want to use Intel compilers for compiling your code. If you want to do that. At that moment, yes, you can man ICC, for example, and see the manual for the Intel C compiler. So again, try to see which modules are available, try to see which versions we have from the very beginning, load the modules, check the new versions, check that the versions match. And now, do this by yourself. So go to 2019, one intro, 05 modules. I have one piece of code just to show you how important it is to use the right module for the code. So this is a small code, that's relatively small, very small actually. Code in C++. So this is C++, not a different programming language. So if you execute this module purge and you try to execute with lambda, you get an error. This is the way, by the way, this is how you compile a code in GCC, in C++. You don't need to understand C++, take that as a black box. Don't pay attention to that. But someone give you that code, and the solution for what you are trying to do is this. They throw you that code, and you need to compile it. You don't care about how it's written. They assure you that it's okay, that offers you the right result, and it's good. And you need to compile that thing. And you try it with the G++ that comes from Red Hat 6.10, and we'll mention that it's no. Have error for that. So now you and you compile it again. No problem. The point is that this function that you see here, or this small piece of code, uses a small trick that is implemented in the, or is part of the specification for C++ 2014. Yeah, 2014. So of course it was not there in 2010. That lambda function was not there, so no, you cannot compile that code with an old compiler. You need a new compiler for doing this. So that is why this tiny little example will show you why it's important to use, what is this stuff? Then you can execute it. Important to use the different modules and check if for any reason you are getting an error. It's probably because you are trying to compile this with an old version of your compiler. If you are using R and you're trying to load modules for R or install libraries, some of those libraries are not available for those old versions of R. So you need a recent version of that in order to work with it. Yeah.
So every time you install new software, you keep the old one and create another mod?
I keep new ones up to a point. So there is always a balance. Having too much is confusing for the people, but at the same time, it's important to offer them a variety of them. So I keep some of them. I start removing old ones. When someone complains too early, I go back and reposition the modules back if there is a good reason to do it. But in general, good codes, there are codes where I trust, let's say they are well developed. By well developed means that they have a stable team of developers, they have test suites, and they are tested in test farms with a variety of compilers. Every single line, they use continuous integration. They are seriously done. So in those cases, most of the time, I can just throw the old versions back because they are well developed, they are well tested. But there are, from time to time, you see there are some codes that they do what they do, but the reliability is not so good. So it's good to have old versions just in case. So that's why. That's why you probably saw some different versions of the same thing, and that's why. Sometimes also Boost, for example, there's a library for C++. They have changed the API, the internal functionality from one version to the next one. So some codes will simply not be able to compile with the new versions. So you have to keep the old ones for a while. Okay. So let's move on. Okay. So everything is clear with the modules, right? Why you use them, how, and I hope you execute this. I put here the trick that you have to apply if you want to use an old version of, a relatively old version of Intel compiler. You have to specify the standard under which you want to compile, because the default standard is slightly different. I think you don't have to do that for newest version. I'm not for sure. So pay attention to those things. Let's move on. With this, we are ready for some exercise for you to compile some codes. I will show you some examples. Again, I don't expect this time, this year, I remove everything that was for hard developers. So no C, no Fortran, no hard coded languages. But again, you receive the code from somebody else, and they assure you that the code works and it solves your problem. So you need to compile it. You need to work with that. So I am showing you some examples of how to compile codes. and they are here. 06. So I'm right here on this location. Intro, the tutorials data, the hands-on intro 06 compile. And here I throw you a few examples using a variety of codes, languages, conditions for you to exercise compilation of them. So for this, I expect you to use recent versions of those compilers. So try to use GCC 8.2, try to load the module for it, keep it there. So that will be enough for the C and Fortran examples. And let's have a look at what we have here. OpenMP. OpenMP is one way to parallelize code using the multiple cores on the same machine. Otherwise, or another way to take advantage of multiple cores that are able to see the same memory. It's relatively simple to program with OpenMP. All that you do is to add some special things like this here and there to parallelize the special portions of the code. So you don't have to rethink or reprogram a lot of stuff. And this is the way you compile this code when it uses OpenMP. So I want you to go here and check that we have this example underscore OpenMP. Let me see what. Let me see which GCC I have. And I have 8.2, should be fine. GCC example opening. Let's see. Throw me an error. When a code uses OpenMP, you have to use an extra argument in the compiler to take advantage of that. The exact line varies between different compilers. In the case of GCC, it's like this. So I would like you to go into the folder and load the module for GCC 8.2 and try to compile that code.
Hey, Guillermo,
Yes?
can you look at the last question in chat? Was that better than I can?
Let me check how I can do it. Well, several things. Oh, okay.
The one above me.
The ICPC, okay, the ICPC is this. Module, purge. GCC typically comes with the operating system. The Intel compilers, you need to load the module for it. So ICPC is the C++ Intel compiler. So if you load the module lang Intel 2018 U4, ICC is the compiler for C, pure C. ICPC is the compiler for C++. I4 is the compiler for Fortran. So if you saw that message, it's because you forgot to load the module associated for Intel. And again, 2018 U4 is what I recommend for you. So you can get, usually you get a little bit of advantage with Intel, but in some cases that advantage is compensated with slightly less stability from the numerical point of view. So be careful and try to check between GCC and Intel, or eventually the Portland. We have also the Portland compilers. So you have several compilers and you can test one another for very minuscule numerical precision, accuracy, or things like that. Numerical stability, basically. So that's what it is for the ICC. For the G++, if you write nothing for them, no input files, is because I'm expecting you to compile the code with like this, adding the file. Or you can do this with a C++, I'm not super sure. Yeah. Probably will compile it the same. So you have to put the file after the name of the file that you want to compile after the G++. Any other question? Oh yeah, okay. So yeah. So don't forget that we have here, what is it? Let's go back. That if you have not done this, go here and execute this to get all the codes that I'm showing you. This is very important for this part because all of this is based on that. So, okay, OpenMP. So OpenMP, a way of parallelizing codes. By the way, it's important for you to realize that parallelization is not something that happens automatically. It's not magically, things not magically parallelized. It requires an understanding of what you are trying to do, what kind of things you can, for what kind of things you can exploit concurrency. It's a different thing. So one way is OpenMP. Very simple, very efficient actually in some cases to take advantage of multiple cores in a single machine. Again, on Thorny Flat, we had machines with 40 cores. So ideally, in a perfect world, something that takes 4 hours or 40 hours on that machine, if with a perfect parallelization, it will take just 1 hour. Perfect, right? That perfect doesn't exist, but yeah, so something to think about. Let me see. Compile code. Okay, so OpenMP, this is a trick to compile code with OpenMP. If you are using the Intel compiler, it would be like this. Same thing. And to execute this, again, let me see. When I compile this, I'm doing it in the lazy way. In this case, I'm being lazy. When you never specify the output, it will create a file called a.out. And I'm being lazy with that. Otherwise, if you want to preserve the outputs in different binaries and not overimpose one to another, use something like this. Put -o, and put the name of the executable that you want to create. But usually I'm lazy with this, and I get a.out. So I execute this, and this is why you have to be careful with this. You never declare how many cores or how many threads you want in your OpenMP code. It will take as many as cores are in that machine. So that means that you will be executing with 16. On a cluster, and you will see this later, you can specify how many cores do you want to use for your job. You can ask for 4, but you still get a machine with 16, but just 4 are for you. If you start executing this, it will start creating more threads than the actual number of cores that you have, and your performance will go down, extremely down. So you need to execute this with curve. One way of doing this is open num. I create a variable. This is one way. Another way is to create a variable and export the variable. But without that, this is one way. I am containing the code. And this is extremely important in HPC for you when you start executing this. If you are having this kind of codes with OpenMP, they parallelize, try to figure out what's the optimal for that code, how many cores do you should request, and contain the number of threads that you will be generating. Otherwise, you will be penalizing you. On a Spruce, we will be also damaging the performance of your neighbor, the person who is also executing on your machine. On Thorny Flat, you are just damaging yourself. We have another system there for contain that. Yeah.
Why do we export that export?
Oh, because this way, this command is receiving the variable is in the same shell. So otherwise, again, if I execute this, it's not working.
Then you export.
If I export this, works. So that's the trick. I did a trick that I often use is do it in one line. So OpenMP num threads and this. Otherwise, I don't get this because if I see this now, I have changed my variable for the entire life of this terminal. So and I've been affecting that. If you want to remove that, you have to execute this to remove variables, environment variables, to clean the variable existence, and you get this back to normal. So for this, it's not a big deal. It's a very tiny code, but for the really crunching numbers, adjusting the number of threads is critical. It depends sometimes on the size of your problem. It depends on the code, the kind of things that you are doing. So you need to test a little bit, 4, 8, 16, and try to figure out what is the best that you can get and where is your sweet spot on that. Let me see another thing. Okay, MPI. MPI is a completely different beast. MPI is in principle, for distributed computing. It's for another kind of parallel computing where you are taking advantage of different nodes, different machines on the same cluster, working together to execute your job. And for some procedures, classical molecular dynamics, you are moving millions of files. In physics, you just move a few electrons, and it's sufficient mass for taking 40, 60, 100 cores in order to do it in a reasonable amount of time. A reasonable amount of time is 2 weeks. So that's what we consider a reasonable amount. So this is a different kind of programming where you have to actually use a library, use different functions, and manage the communication between the different processes involved in that in order to get your result. How you compile this code is a completely different story. For this, we need a different compiler plus an MPI library. So imagine that we are right here on your version, pristine. Try to start with the pristine version. So module, load, length, GCC, parallel, OpenMPI, or GCC 8. There will be enough. So I am adding the GCC compiler, the GNU compiler collection, and the OpenMPI. The OpenMPI is a special implementation of the MPI infrastructure for us for parallel computing. Again, if you are not too much into HPC, probably you don't care about this. When you compile, let me see what we have here for compilation. Oh yeah, okay. We have this code, example MPI. I will try to show you how to compile that. GCC, you compile with GCC example MPI. You get a bunch of errors. Doesn't know how to do with that. Doesn't know how to do with those MPI things. You need to compile it with a wrapper for MPI. And the execution is also different. You need to execute this with an intermediary program that manage the coordination, the logistics of activating several processes eventually on different machines to execute your program. I am doing a small exercise here with just 8 processes that currently living on the same machine. Doesn't need to be that like that, but this is how that works. MPI run, I'm asking, okay, I would like to create 8 processes. They will communicate to each other. They have to get the job done. And those processes could be in 8 different machines. It's perfect to do that. Okay. The compilation and execution is different. So again, I'm showing the example here. And this is kind of a little bit more advanced thing. If you are using the Intel version of compilers, the Intel suite module, and this is important. Not many people know this. They become confused with that. I think it's important to mention that. Module, load, length, Intel 2018 U4. So the Intel compiler also includes an MPI implementation. They have their own MPI implementation. And they offer you 2 sets of wrappers. This one is sit on top of the Red Hat GCC. So it's the Intel MPI on top of GCC. Same thing happens with this MPIC, the C++, the Fortran 90. Yeah, all of them are on top of GCC. Or they offer their own version of, so the MPI on top of their own compilers with this. Okay, it's a different story. You have to select which one you want to use. So I offered you here a table with, I show you, okay, this command, if you are using the module for Intel, this command is actually for this language used on top of what? On top of GCC, on top of GCC, on top of Intel. Some people get confused with this, and this is important because, in particular for Fortran, you need to decide which compiler are you using underneath in order to use certain flags, for example, for MKL, for the linear algebra infrastructure. So we will mention that there. This is another code. Another code. I give it to you. This code. Let me see what is this. Okay. This code is using here a library that comes from something called LAPAC. No, this is LAPAC. That allow you to solve some linear algebra equations. Let's keep it like that. Linear algebra. Whatever you know about linear algebra is doing something with matrices and vectors and arrays. And in order to compile that, you need to select some version of linear algebra behind that. So let me see. Let me, now that we have this here, that I load this model, let me do it with the Intel version. Oh, yeah. ECC. Oh. So this is the Fortran compiler. And I just compiling this routine. I need this routine because I would like to have real pseudo random numbers. Good pseudo random numbers. So I compile that. My routine is there. How I know that my routine is there is because you saw here this file. This file. So this is the product. This is a binary thing. This is not something that you're supposed to read. You can read this. This one is okay to read. I don't. Well, this is Fortran. It's okay. This is Fortran. Text file. If you understand Fortran, it's okay. You can read. But this one is not. Another thing that is. So this command file on top tell you what the file is, what it's all about. This is a binary file. This is not a text file. This is a product of compiling this routine into a binary code. And now I can use this long command here to compile this code, example DGSP F90, using this object file that I compiled a minute ago, with this linear algebra line. And this linear algebra line is complicated. Usually, what I do all the time is going into this, the MKL link advisor, and start feeling what I need. If I am using this compiler and I'm using this other thing, which kind of version, if I would like to multi-threading or not, the sequential, I select all those things and I take the output of that and copy and paste that. For the most part, this is, once you know this, you probably get it. But this is using is the Intel version of NKL in sequential version, the sequential version. So just one thread. And that's it. This is the way you compile code that is written with this very often used linear algebra. So even when you are using Python, underneath that, we will see that a lot of time you are using this, LAPAC and BLAST, without realizing. So a lot of what we do in scientific computing, a lot of things are done is basically linear algebra. And even more today that people is in the mood of neural networks, those things are mapped into linear algebra problems. So linear algebra is really, really important in scientific computing. And these BLAST and LAPAC are the standards for that. HDF5, another example. you can see that. I will move a little slightly quick on this. This is a very efficient library for storing big amount of numerical data in binary files in ways that keeps on the structure. So imagine that you are storing cubes, or you are, imagine that you are simulating the collision of neutron stars or black holes or things like that. Is basically filling a big cube of numbers that represent the fields and the conditions of those stars. And those are huge amount of numbers. And one efficient way of storing that amount of data is with HDF. And this is the way you load the module for that. Let's see if I can. And if you try to execute it right away, it will fail. I will not do it. You have to declare the library here, LHDFI, in order to compile this code that uses HDFI. So it's okay. So just keep in mind that this is a library that will have. Fast Fourier transforms. Again, this is something that for some areas it's often used. The standard for that in many cases is this one. Intel also provides for this one in particular. So here you see those functions here happening, where they are preparing a library, a plan, and executing the Fourier transform. Let me see if I can do this. This is nice. I will combine this. This is this. So again, look at what I'm doing right now. All the time that I would like to compile a code, I am loading the module, a good module, for the library that I'm using. In this case, HDF5. In this case, FFTW. I always mark which is the compiler that is used for doing it. It makes a good match. And then after that, I'm compiling the code. In particular, this one, I can execute this. Oh, no. And this one is basically taking a bunch of points in reciprocal space and is converting that into Fourier space, if you understand what. So basically, I'm getting an image after that, and this plot is doing that. This script that I put right there is creating the image. Let me see if I can display that. Oh yeah. And this comment helped me to plot images that I create with Python on the cluster, and I can see those. So this is what I did. In a few places, I put some dots. With the Fourier transform, they are converted in weights that contain the same data basically in a different space. Consider that as a change of base, change of representation. And this is the result of that. So waves. And the direction of those waves is related to the positions of those points in the space. I will not go into details on that, but the important thing is you saw that I load the module that I need, I compile the code, I execute. For executed the code, I also need to load those modules. So every single time that you compile something with module, you usually need the same module during execution. You need it for compilation, you need it for execution. There are exceptions that in most cases it works like that. It depends how you compile it, actually. So the exercise is basically take this one, for example, and try to compile it on the cluster. This one, GSL. You don't need a special library for this because the GSL is included in the GCC 8.2. So I included there. You can try to compile it. I will show you the final result if you get stuck in that. So let me see that. And I will give you a few minutes to do it. So the GSL is the GNU Scientific Library. It's another library that allow you to give you some nice things. They have special functions, Bessel, Legend. They are able to do some integration, numerical integration. They are able to do a few things. Again, imagine that you get this code. You don't need to know the code. You just need to compile it and execute it. So this is what you have to do. Okay, I'm using this. If you just, you will fail. Okay, how is our time? And consider taking, let's say, 10 minutes to relax a little bit. And so we will continue at 3:10, and it will be fine. I will show you the last part, the job submission.
Here, man. Someone was asking if you could go give like a general idea of what compilers are used for. Like, what's the purpose of them?
Okay. Okay. There is always a trade-off when you use a compiler. For one side, you want something that it runs efficiently, so quickly. For another side, you want something that runs accurately. And efficiency and accuracy also reach a confrontation point at some level. So some compilers take some risky alternatives when they are converting that into binary code. Those risky alternatives could be damaging the accuracy of the results. So what usually you should do when this becomes an issue, when accuracy is really important to you, is to compile the same code with different compilers and different optimization levels. So let me see this. I don't have any example here with will see this. Let me see. Okay. You probably will not see this for this small code. It's too small for seeing any difference, probably. Except, okay. First thing, this example. Let me see if I can do something. Well, maybe I can do something about this to show you that with this just, I will take that, try to take advantage of this one to see if I can tweak it a little bit to see something. I will change the size of the matrix a little bit. So let me see if I can. So now I'm creating a 4,000, maybe it's too much. Let me see, 1,000. I want something quickly, but not that quick. So this is 1,000 times 1,000. This is a matrix, and I'm basically solving a linear equation problem with this library. I'm filling this here, the matrix, with random numbers. And here, what I'm doing is, okay, the library, and I'm doing the composition. So let me see how good it is. This is actually how you compile this piece of code. And I will compile it with no optimization at all. That's one thing. The first thing is same compiler, different levels of optimization. And this is something, let me see if I can get a timing on much. Well, there is a problem with this. Most of the time will be just writing the whole thing. I need okay. No. Okay. Okay. First one. Okay, so I tweak a little bit the code to work with a matrix that is 3000, 3000, solving the problem. It will take a few seconds, hopefully. Problem is that those things are not linear, so I have difficulty thinking non linearly how much it will take. So I don't want that slow thing. Maybe this one is better. Okay. Okay, so the first thing is to test with the same. Okay, this one is good actually. Yeah. Okay, no optimization at all. GCC, 17 seconds. Okay, and the first level optimization, 01. Usually it's when it's a big jump. If you use O3 all the time, in some cases, your code becomes numerically unstable. So you can, at some point, for very, very complex operations, it could reach post locations where you are dividing by 0, where you are dividing for extremely large numbers. So, or the divisions are not accurate at some point. The exponentiation is not giving you the right numbers for floating point precision. So you can start getting deviations from the good result. That's the danger. But you always have to control that somehow, how sensitive the code is. In real applications, what people do is that they check that some portions of the code is really sensitive to those things, and those are compiled with lower optimization, and the rest of the code they consider safe, or yeah, it's okay, and they compile it with O3. Yeah. So this one was 15, and this one. Again, this is just very quick example how you, every single time that you increase the optimization level, the time goes down. But again, I'm doing this. Many people is probably using the head node, so I am competing with others. You see, I am increasing. I'm getting slightly the wrong. O3. If I want to do this seriously, I have to do it several times, and I have to go into a different machine, creating a job. That's exactly what.
I wasn't here.
Okay, let me see how this one. Yes. You see that it's the line there, and I was displaying how those O3 change the level of optimization to make it go faster and faster and faster. So this one is just, let's say, the standard solution. For your code, that your code is smaller. So what I did was make this matrix instead of 4 times 4, I made the matrix 3,000 times 3,000. So big matrix. So the code procedure takes a lot of time. And the O3 or 2, all those optimization change amount of time that the computer takes to get the result.
So this is for this.
For this is this solution. This is what you have to do. This is why the library is this one, and this one for the C version of that. So this is the solution, and you don't need to go there. So this one is actually loading installation, compile it, and execute.
Then I want this one.
This one, no, I probably took it out. I removed that. You don't have.
So I have to.
Sometimes you need some libraries. The libraries, you need to know which library. And I showed you examples for different codes. In general, you don't know which libraries you have to use. Go into the documentation of the library. It's not so simple. But I show you was a very, very simplified version of the whole story. But you get kind of exposure to what it means to compile a code. But that's what really matters to me. That you compile something. But don't worry if you don't get it. It's not that. That's not it. So this one, 16. Anyway. So this is one thing, again, I'm not doing this seriously, and I'm competing with you if you are doing this, with all the people who is doing this online. So, and this is one thing. Another thing that changes, let me see if I can do this. Okay. Okay. I'm getting a little bit better. But probably I did something wrong. So one way to optimize the codes, this is a lot of the time my job here is optimize codes very, very efficiently. So this is one thing, the O2, O3, O1, O2, O3, and checking, hopefully when developers do their good job, they have tests with references. So I can check how my numbers deviate from their reference. So one thing is to have a good code that is fast. Another thing is to have good code that is fast and accurate with the result. Another thing that you can do to optimize code is to use this merge. This is tricky and on Spruce, because on Spruce we have machines with 4 generations. So we have Sandy Bridge, Ivy Bridge, Haswell, Broadwell. So they span 6 years of Intel industry developments in processor. So if you optimize for the Broadwell, they will crash on basically any other machine. And if you optimize for Sandy, you will perform really badly on, let's say, you will not take the advantage of the Broadwell or Haswell. This is different on Thorny Flat, with all the machines are at the Skylake, all the machines are exactly the same. So I can optimize just for that architecture, and I can get 40, 50% extra performance just for tuning that for that specific machine. So again, the manual can help you with this. I was actually doing the wrong thing, because the machine that we have on the Spruce, the machine where I am right now, is an Ivy Bridge. And so in fact, I should be optimizing for Ivy Bridge at that moment. So this is what I'm supposed to be doing. To optimize for this machine.
The model.
Yes, this is an Ivy bridge. If you execute cat proc CPU info, you get something like this. Let me see if I can. See. Why?
It's on.
Yeah. So if you go here and you paste this information here, hopefully, yeah. Which is KP2. Is this? No, it's not this. No, it's not this one exactly, but it's this one. Okay. So Ivy Bridge. So you can go and check with the reference of the processor that the processor is Ivy Bridge, and this machine. So the generation is Q3 of 2013. So you can see how old this machine is. So. So I am tuning for that machine. If I execute this on a sandy machine, on a sandy bridge, it will probably crash. It will do something and then crash and kick me out. So again, and this is for one compiler. And the question was also for another compiler. Why you use another compiler? Intel usually optimize better for their own processors, so you can get an edge on that. The NKL, the math kernel library, is really good. It performs good. So you get also that advantage. In general, they perform better, but my experience is slightly more unstable compared with GCC. So these are always a threat. Another thing that you need to know is that the optimization levels in Intel and GCC doesn't mean the same thing. So O2, they have all the same thing. They're all 202, but they doesn't mean the same thing. The tricks that they apply here are probably not the same tricks that they apply here. So you cannot compare both things with just that figure. So that's something to take into consideration. Okay, let's move on to the next thing. This is probably the most important thing for today. In order to reach this point, I have to show you all that I show you during the day. It's how to submit jobs in a cluster. And this is how this is different from your machine, your desktop. Your desktop machine is yours. You typically have your machine, nobody sits on that machine. If you are there, it's just for you. On a cluster, it's not like that. We have 300-400 users, and at some point we can have easily 30-40 users concurrently using the machine. So how we manage that? The idea is that we have to forget about executing my stuff right now and simply indicate the machine that I want something to be done, deliver the instructions to the machine to execute that when the machine sees that fit. They have time for doing that. And when the job is done, you receive a message on the mail, the job is done, you get the results. This is how an HPC cluster works. You submit jobs, you get results. You are not supposed, in most cases, to just do it interactively. Right now, no. You execute, you forget. Tomorrow, in a couple of days, you will get the results. You don't care. That gives you the advantage of executing 100 times, 100 jobs, different jobs. You need to align 100 genomes. You submit all of them at once. You have 100 jobs, all of them will start working. When there are enough resources for doing that, you get the job done, you get the message, you analyze them later. You cannot do that. Yeah.
Should not use this strategy now to develop our software. Use another machine to develop and then.
Typically, yes. Typically, you develop in a different machine, you test it on the cluster. That's how it usually works. So, except if you are you can do exploratory things, which I will show you that how to execute things interactively. But no, in general, you just, for most part, you just submit jobs, you get the job done, and you post-process that on the machine or on your computer, on your home, with the data that the job produced for it. So, okay. There are several resource managers and schedulers and machinery for this. There is a variety of them. We use this one for both of our clusters, Torque as a resource manager and Moab as a scheduler for moving the jobs for all our users. Easily, we get 1,000 jobs at some point in time being executed on the cluster. No problem. 1,000 jobs, 2,000 jobs, no, not a big deal, right? There are a set of commands that allow you to control submission, deletion, when the status of the jobs, how they are moving in my cluster, what they are doing, execute several jobs at the same time. So, and I'm showing you just all the lists of commands, but I prefer to try to do this with examples. So let's forget about the table and let's do this for real. So what about, let me see, probably create this. Okay, well, I will do this one right now for, oh, okay, I can do this. Remember that I was doing something like this before, so let's go to source 6 compile. And I was doing this, right? It took 15 seconds to give me the result. So let's start working on this. Let me clean the environment a little bit. Let me clean. I would use this as an excuse to start working on my first job with this. So you can use this in example.gsl if you want. For you will be 4,004, very tiny thing, 4 times 4, I think originally was. So now we'll copy this. I will copy this. So I will compile this. I copy and I compile this. Probably I don't want to do this. But anyway, I have my code. You see, I have my executable. And I was lazy and I created the executable with the standard name a.out. And I will start creating a job for it. I need to execute this, but I don't want it to execute it right now. I just need this to be executed in the cluster, get the result, and when the result is done, it's done. So this is very minimal. Let me see. I will do it with nano. Run job. Okay. Okay. The first thing, which modules I currently have on my system? I have a bunch of them. For this, I don't need this, so I will clean a little bit this one by one. This is something that you can do. I was not actually needing this, so I'm not using the input. I'm not using this one right now. I'm not going to clean this. I don't need this one either. Actually, I don't. The only thing that I actually need is the only module that I actually need is this, for what I did. But let me show you what happens when you make a mistake. No modules, not modules. I compile the code, but I exit and I re-enter. I have not loaded the module, and I have this code there. Now I execute this. Let's see if that works. Oh, it's still working. Probably compile it statically. Probably. Oh, I was lucky. Typically, this is not what happens. Oh, yeah, I got it right. The reason for that is, in most cases, not for this super simple case, the libraries the final executable depends on the libraries that you compile. So you need the modules that you use when you compile it in order to also execute the code. In this particular case, it was so simple that he found another alternative for the GSL, and they was able to manage with that. And the code was too simple. So, but typically, what you like is to load the module during execution. So that means that this line should be also part of the submission script. This script is two things at the same time. It's a perfectly valid bash script. It has the magic on the line, very beginning. For the purpose of bash, those are comments, so they don't matter. Those PBS things. From the purpose of a shell script, those are comments. They don't care. And this is what I should want to execute. I would like to load the module. I would like to move to the folder where I am executing this. This is the trick to do that. And I would like to execute my program, a.out. So I am indicating what I want to do.
What's the PBS?
Those are special lines that, again, are comments for the bash.
The other PBS.
This one?
CD, yeah.
This one?
Yeah.
This is a variable that is an environment variable that when you execute this with the queue system, receives the location where you execute the command. Because when you execute this in a remote, in your machine, you start on your home folder. But we are not in the whole folder. We are inside this 2019, blah, 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 blah. So we are in another folder. This trick allows me to jump into that folder at the very beginning. So this is a different thing. This is something that the command that we will execute in a minute reads in order to figure it out what are the resources that you need, that you want to execute this job on the cluster. So for this case, I am telling the system that I need one node. I need to execute this in one node. I just need one core of that node. So give me just one core. I don't care. You can give the other cores for other people. I just need one. We may call this not parallel. I will not take advantage of having 16 just for me. And I need 30 minutes. 30 minutes is too much for me. Remember that all of our executions was a few seconds, 17, something like that. So let's be conservative and let's say I need 5 minutes. I need 5 minutes for it. Let me see, email. I will put my username. So I get, when this is done, I will get a message on my mail system. And this one is to give me a mail, send me a mail when the job finished. I need a job name. I would say this is a test GSL. I put a name for this. This is after the N. And this is something that I use often. Use this. I call it the Joe command. Basically, it attached together on the same file the error and the output. Otherwise, it will create separate files and it will create too many files, and I don't want to see that. I just want one file that contains whatever the output of that command produces. I want it just there. So, and I would like to use training, right? Training. Training. So I ask you to use something like this. To start writing. This will be your first execution of
What's training again?
It's a queue. I will show you that. I will show you what exactly it is. So what I can show you to split this properly. Let me see. Okay, I will do a trick here just to show you this and at the same time explain you about the queue and all this stuff. Control X, Y. Okay. So this is the okay. So on this side of the world, this is what I would like you to have on your file. I typically name my files, my submission script, runjob.pbs. That's me. You can put whatever name you want for your job submission script. And on this side, I will explain a bit about the queues. Queues are very similar what you see in Walmart and the supermarkets. They have several places where you can pay for your groceries. And what you do is to select one that is good for you. I mean, they have usually one for 15 items, the quick one. It's supposed to be for a small amount of purchases. So this queue move fast. You can see 5, 7 people, but you know that this queue will move fast. There are others that are for big purchases. So even if you just see 2 guys in front of you, it will be a pain. You will have to wait until all those groceries move forward just for getting your turn. So it's the same thing. Yeah, the command for see that is just that. Well, probably it's not really nice when you see this from this perspective. we have a bunch of queues. Let me see how we get this. You see, most of the queues that really matters to you are those that start with com something. The queue for a standby, that is a queue for 4 hours, using all the resources that are idle in the system. The queue for us during this training, it's called training. What is this? Do you say training around?
Training.
Ah, right here.
I wish I was mapped that order.
Yeah, anyway. So this is a queue for training. Apparently someone submitted already a job. Okay, good job. There is one job here that someone submit. So you see the people start submitting jobs. And right now we have what? We have, for example, this queue, this queue for a week. We have 157 jobs right now on that queue. 93 are in queue, 93 are waiting, 64 are in execution right now. So they could last 1 week, those operations. This one is standby, we have 30. Usually it's not that low, but we are in vacation, so well, let's see. When graduate students return, this things change. And all of them are in execution. So what else? This one, okay, this one professor, yes, it's on queue, they have quite a number of jobs. Again, this one, and this one, okay. The usual suspects here are there.
I have a question. So what
Yeah.
if they're all zeros for someone? Are they?
Those all zeros is that, for example, this admin queue, nobody has executed jobs on that queue. That queue is empty. You have no permissions to execute in the admin queue. I have permissions for that. Most of those are for professors. They own their own queue because they own their own machines. So PIs can buy nodes and they get priority on their nodes. They own their own queue and they can submit those to their own queue. So those queues move faster for them. They basically own the machine. If the machine is idle, if they are not using the machine at that moment, the machine goes for usage to the standby. So everybody can use it up to 4 hours. So that's how we manage having resources that someone can use with priority, but anybody can use if he or she is not using it at that moment. So what do you see?
If I don't have a machine,
If you don't have a machine, if you don't own anything, all that you can do is work on the com. This one is the community 2056 gigabytes of RAM. So this is a large memory machine. This is a queue for date. There is one here for GPUs, the commune GPU, where you can submit jobs. There are 3 jobs here in execution, submitted, 3 in execution. So
I need to specify that.
Huh?
I need to specify.
You need to specify. If you don't specify, the default is standby. The default queue is standby.
Okay.
It's this one.
Take a long time.
4 hours. They give you 4 hours. So you cannot ask for more than 4 hours.
And standby.
Standby.
Up to.
Yeah.
Unless we can talk, not want to get too much off topic. We have another system called 40 Flat that's much larger than this one. That has a lot more community resources. When we say community, they're free for the whole state. That's not just the U.S. Marshal. That's anybody who uses your computer. It gives all those people. These other queues should have names. That's actually their W login names that they have. They actually pop notes. They get dedicated resources. It's not a requirement. It's just if if you decide for your research you don't want to wait, or you have special requirements, when they get funding to do so, they buy those. There is no requirement to buy those. Basically, here was always the best thing he asked is, do you want to pay for time? You're paying for waiting. So if you're paying waiting, you can make. Sometimes you don't have to wait at all.
Okay. So I reordered this with a small trick. These are the set of queues that even this one, so all those, plus standby. Those are available for anybody. So for this training, you have your own queue with some reservation, so nodes that nobody can use, just you, for executing those things.
Why, for example, people chose to use Squeak instead of Date, but they don't have a.
If your job, if this is something important, you should start getting a knowledge. Only you can get a knowledge how long a job will take to complete. If your job, you know for sure that will finish in less than 1 day, it's probably much better if you just submit it to the day queue. The week takes a few days, even a week, just to get in. So why you want to wait? If you can submit into the day queue that move faster, the jobs are not longer than just 1 day, and you get your jobs moving.
You're actually penalized for the community queues. You're penalized for longer using it.
Exactly. So you ask for something, you use it, your priority will go down. It will take longer and longer and longer to get your jobs into execution. So this is important. So again, imagine those are like several lanes for moving your jobs. You should select based on the amount of time that will take. And if you own your own queue and you want to get this quickly, you have your own machine and you have your own queue and move it there. So let's go back here to this one. So this is the code that I would like you to write.
So, is that in what?
So let me go. So I create a file called runjob.pbs. I'm using Nano because it's just the easiest for you to get something. So I create a file with Nano and I write this. What we're explaining before, and you can forget about this. What is this K does? Nate, you know?
What's that?
The first this K.
I'd have to look.
I don't remember.
I
You don't need it. Forget about that line. One line less to write. I don't know what it does. So I am asking for one node, one core, 5 minutes, right? I want any message to be sent to my mail. I put this name. I am using the Joe to merge output and error files into a single file. And I would like to use the training queue. This is the most important thing. If you really want to use this system for non-interactive execution, most of the time this is what you would do. This is the way. You have to write this file. You have to know how to do it. In most cases, you keep a template and you change a few things and you move, and you don't care. And this. So after you wrote that file, you say, okay, yes, yes, yes. And I compile the code. I have the code already compiled. This is the .a.out. And I want to submit my job. So please try to do this, follow this, and I will submit my job right now with this command, QSub. This is the most important session. It's late in the afternoon, you are tired, but I have to show everything else to reach this one. And just to meet you, John.
Don't I need to test this file before submitting?
I test that you know that I tested with -02, -03. I tested.
I know, but I mean, the run job .ps. Because if I put some wrong,
if you put rubbish, it will fail. You will know that it will fail. You can resubmit.
Yeah.
It's not a big deal. You can make mistakes with this. I do mistakes all the time, so no, it's okay. You get a number. You see that you get a number here. This number identifies your job. This number. You get a number. You get a different number every single time that you execute this. Right? So I would like to see my job, the status of this. This is one way of.
You guys have questions? Y'all here, Dave?
Yeah. Look at my jobs. Well, it's so quickly that typically what happens is I see the job first with a Q here, after with an R when it's running, and a C when it's complete. But this is so fast, and they give us plenty of computed resources, so we get super quickly on execution. And, huh? So yours is in Q. Why? Is it still in Q?
S.
You execute again. You can execute again to see.
Still.
Is what?
Still in the queue.
Maybe to us you are for too much. Which Q are you using, or? Give me the number. Give me the number. What is the number?
46147.
Wait. 461 471.
4623.
62. Okay. This is another command. Oh well.
Now it's finished.
Oh well. But I cannot do it. I forgot that I cannot do this. I am not allowed to see you what is happening with your. I can do it just with the root account.
Now it's finished. I got an email.
You should get an email, and you will probably got a file like this.
That's okay. It's a little. If you ever get something like that, just like this, us.
You see a file like this. Test the name, whatever the name you set up for your job, dot O and the number, the job ID. This is called the job ID. You should have received a file like that. Do you have it?
Where?
Exactly in the same place where you execute the. Okay, I will have to start looking at that. Let me see what it does. Mine. Yeah. Mine is not doing much because I'm not even showing my own matrix, but let's see.
Yeah, we should know that.
let's see. Well, if you finish it, let's see. So, okay, in my case, it's not showing much. In your case, you will see your matrix, the tiny little matrix 4x4. This, and the inverse matrix, and that's it. So at this moment, you have executed your first job. I hope you got the file. So again, you can see a few things about your job. What was mine? Okay. Check job. For a couple of days, I think, 2 days, I think, you can see some statistics about your job that could be interesting. And the reason why this is important, I have seen this, for example. They execute this command. Check job -v and the job ID. Right. You see, for example, the time that the job start, the status of the job. If it's in queue, it will show you in queue. If it's running, it will show which node that was executing your code. So it's very likely that everyone got a different node. Some of you probably got the same as mine because I was sharing with you the same machine. I asked for just 1 core, but most of those machines have 16 cores. So at least 16 of you will get exactly the same machine as the same machine that I got. And it will tell you, what else? For real things, for real execution, it will tell you how much of your processors were actually used. Sometimes the amount of memory, not this one. So especially the timing is important to know. In real life, what you do is to execute once. Imagine that you get some task. Usually during your PhD, it is not just one task. It's something that you have to do 100 times. So you do it first, the first one, you get an idea how much it will take, and you explore that. So probably you overestimate the amount of time, underestimate. You try to get an idea the amount of time that you need to get that job complete. And with this information, you can target next time for the rest of the jobs the good queue that you would like to use. You don't want to ask for the day queue for something that takes 2 days, because in the middle of the execution you get killed. And you get killed. If you ask for 1 day and you cross the day, your process is killed. And you have to do it again. So it's better to try to be conservative on this. And if you realize that actually you don't need that amount of time, and if 1 day is okay, or can you tweak things to parallelize a little bit, where you can play with the parallelization, and you can ask for more cores and reduce the time so that you can get into the 1 day with some flexibility, with 10, 20% extra, just in case. And you fit that to all your jobs, you can move it in the day queue. Even better, if you can parallelize so well that you can get it this in less than 4 hours, much better, because the standby queue moves super fast. So you get a lot of jobs moving on that queue all the time. Let's see a little bit more things here. Well, yeah, and now they said, what is this? Yeah, I never use this actually. So, this is one example of something that uses this in parallel. Let me see if I can, oh, maybe I can do this. Yeah, well, we don't have time. Maybe there's, or in these few minutes, try to do this with the MPI code that we compiled a minute ago. So here, I show you, let me see, here that we have this example MPI. So go, as an exercise, go into that folder, I am right here. Go into that folder in the compile and try to create a job for the MPI version. It's exactly the same. This is the recipe, basically. You compile that. All that you have to change is, well, how many cores you plan to ask. If you want to ask for 16, it's okay. You can ask 8, or you can ask more. And in that case, you need to ask for more nodes. So you can create a job for 2 nodes, 32 cores total, and having that job done, parallelized for you. So this is basically the exercise. In these few minutes, let me explain you this. This is a little bit more advanced. This is called a job array. Some people use basically the same template of execution, but they have to do it for 100 cases. They often, people in genomics, they often do this. So they have to align a lot of genome. It's basically the same thing over and over. So one single submission script can help you to work with all those cases. You don't have to create 100 scripts. You're supposed not to do that. The trick is very simple. The trick is to use something like this, where you, with this T, you select on the range of values that you want. This end up with a variable here that changes, that receive. So for example, if this range is 1-10, you are creating in just one execution 10 jobs, all of them. One receives this variable with the value 1, another one with the value 2, 3, 4, 5, 6, 7, 8, 9, 10. So, and you use that to change the execution, to apply that, for example, for alignment, for genomic alignment, for the first genome, for the second genome, for the third genome, 4, 5, 6. Or you are changing parameters. You are cracking cells, and you are simulating a fracture. And you would like to simulate that fracture under a range of temperature. So again, you can use this to change the variable, one variable that makes sense to you, to change those that and associate that to different temperatures and execute for all of them. This is very, very useful. I have here an exercise for one code. That uses that. Probably we don't have too much time for actually giving that for doing it. That uses one code, so you don't have to pay attention exactly what the code does. It's encoding physics. It's simulating some material, and basically what I'm doing is to associate this in making 5 different executions and moving them with just one single submission. Without entering too much details, there are more variables that this associated to PBS. I show you this one to change into the folder where you submit. And I mentioned this one for the array ID, for the job arrays, that you receive different number on each individual execution. But there are some others that you can play with. You receive those variables every single time that you execute. And the last thing is to, well, a few commands, qstat, show you all the commands that are right now on execution. Some of you are executing this, probably, I see this, complete training 23, complete some jobs here. And you see all the people is executing jobs right now. I don't know how many. What? So how many? So we have right now, maybe I'm wrong, but we have a little bit more than 300 jobs in execution right now in the cluster. When you see 300, we say the cluster is empty. 300 is not. So it's okay. Let me see. Oh, this one. Oh, yeah, we're right in time. And this is something that is a little bit more advanced again. You can create a few files called prologues and epilogues that run before your actual execution and after your execution. Typically, this is more for debugging or for a special execution, where you need to clean some environment after the job is done. There are ways to do to get some extra performance, moving files into special places. So with this couple of files, for the prologue and this one for the epilogue, you can get some extra information about the environment, the amount of memory that the jobs took, the resources that it took, or eventually cleaning some places with garbage that was left behind by this mission script somehow. And all that you have to do is to put this kind of commands at the very beginning of, inside your submission script. Again, that is a little bit beyond what is expected. And finally, interactive executions. For example, you want to play with something here. So maybe see if I can see this. You want to execute something interactively. You want to explore. So this is the way to execute something and receive a machine for you to work for the next 4 hours. Something, I don't know. What's the length of the training queue? 4 hours?
Training is.
Oh, wait, okay, anyway. So you just have to wait a few minutes, typically 2 or 3 minutes to get in execution, and you receive one machine. You receive one machine, and you can start executing things. And those things could be R, if you want to use that for statistics, for data mining or something. You can start exploring. You can execute Python. You can, this is actually what we will do next week, using this system to interactively exploring how you program Python. So if you need to do this interactively, you can do it. This is not typically what clusters are for. This is not typically how you use clusters for, but this is something that you can do. It depends how busy the queue is. And there is, okay, they give me a machine. You notice that I got a different machine. I was here. After the execution, I got a different machine. So this machine is perfect for me, for example, to start exploring the optimization, because nobody is executing in this machine. Nobody is using at least one core, and I can request the whole machine if I like. device one to get one machine just for me.
Because having the same machine.
I have the same machine too.
Yeah, you probably, I never specify the number of cores, so by default, it's just one node, one core. So you probably got the same machine. It's okay. So right now I can, for example, do this if you are not module load lang Python 37 something. I can start executing, exploring with IPython things with my data, moving my data and playing with that. And I got a very decent machine to do this. So I can start doing things. It would like to, I never actually execute the command to export X11. But if you execute it right here, if you enter this way, if you are using MovaXter, and you put this extra command here, you can actually create plots and get those plots on your desktop machine to see if everything is fine. Closing, getting different plotting, playing with that, exporting those plots into figures, and those are ready for publication, and it's perfect. It's all that you need. So this is another way of working, the interactive. And tomorrow I will show you some ways of actually using interactive with graphic user interface. So you can play with RStudio if you are familiar with that, with the IPython notebook. So you get that in an environment that is familiar to you, on a graphic user interface environment, and you can basically request one machine for you to work and do whatever you want to do for your research. But okay, we close this. We move into more advanced topics for tomorrow. Okay?
Thank you.
So once it kicks me over to the other machine, I have to log out twice.
If you are interacting and you don't want to work anymore, you have to leave that and leave from the head node, so you leave twice. Otherwise, you just wait, and when the time expires, you get kicked out of that machine. So you have to stop that.